Okay, well, welcome everybody to, I guess, the afternoon session in Cambridge. It feels like morning here. I guess really early morning for where Sophie is. So Sophie Libkind is our first speaker. She's from Stanford University and will be speaking on operatic modeling of dynamical systems, mathematics and computation. Thank you, Sophie.
Great, thank you so much. So I, along with my co-authors, Andrew Baas, Evan Patterson, and James Fairbanks, are really excited to present our work on operatic modeling of dynamical systems, both the mathematics and the computation. So to sort of set the stage for this work, I like to think of the work that applied category theorists are doing, and in general applied mathematicians, as this work of finding the right abstractions. So going out into the world and noticing patterns that different types of scientists and engineers are using, and distilling those patterns into mathematical objects that then we can make definitions about and generalize and write theorems about. And so sort of a second part of this finding the right abstraction is implementing the right abstractions. So turning those mathematical objects into computational tools or other implementations that are really useful and practical for scientists. And so some of the recent work in CatLab and the algebraic Julia ecosystem, which is a programming sort of ecosystem of different packages in the Julia language, has been implementing the right abstractions that applied category theorists have been finding and working with for many years. And so this talk is sort of all about implementing the right abstractions, where that right abstraction is compositional dynamical systems, which again is something that applied category theorists have been sort of discovering and working with for many years. So to sort of zoom in on that right abstraction of compositional dynamics, that sort of starts with this observation that systems have modular structure. So if you have a complicated dynamical system, maybe you're a scientist working with hundreds of different species in an ecosystem, you probably can't keep track of all that data, just like all of those interactions off the top of your head. And so to make it sort of more wieldy, what a scientist will do is sort of create some informal modular structure. For example, breaking that ecosystem up into land animals, river animals, air animals, and water animals. And then sort of understanding the structure, the dynamics of each piece, and also the interactions between the pieces. And so another example of this might be something like a multi-city SIR model, where you have many single city SIR models. So each city has its own susceptible, infected, and recovered populations. We're thinking about an epidemiology model here. And these systems interact because people flow between cities. So people move from city 1 to city 2 and city 2 to city 3. So this is sort of the big idea of compositional dynamical systems. And so sort of the main idea that I'm really excited to present today is sort of the correspondence between these three different worlds. On the left-hand side, we have this world of the modeling sort of terminology or intuition. In the middle, we have this world of mathematical abstractions where applied category theorists have taken those intuitions coming from modeling dynamical systems and turned them into sort of formalize them into often operads to describe the syntax of composition and operad algebras to describe the semantics of composition. And finally, as part of the algebraic Julia ecosystem, we've implemented a package called algebraic dynamics, which turns all of those mathematical abstractions into really executable code that scientists can now use to build and analyze these compositional models. So the outline for my talk today is really to sort of give you a taste and a flavor of this table and how each piece works and how they interact together. In algebraic dynamics, we've implemented two distinct types of composition. The first type is undirected, which I think of as sort of being a passive interaction between systems, where systems interact by passively sharing resources. And we're going to spend sort of the most time on this example, really sort of digging into each detail of this table for it. Then we're going to move on. The second style of composition that we've implemented in algebraic dynamics is directed composition, where systems interact by sort of actively sending messages to each other. And we'll sort of do a quick drive-by of this, but pausing to sort of highlight the features of algebraic dynamics. And finally, we'll conclude with the other contributions that we've made in the paper, as well as some future work that we're really excited about. All right. So we're going to start again with undirected composition. And a lot of sort of the mathematics for this part of the talk comes from, or is grounded in this paper by John Baas and Blake Pollard in 2017 about the composition of chemical reaction networks. So to give you a flavor of how this undirected composition works, suppose I have sort of, I'm a person studying an ecosystem, and I've sort of identified 3 elementary models of my system. So the first elementary model is going to be a model of rabbit growth. And so we have a population of rabbits, and it just grows according to some rate beta. I have another model that describes fox decline, so how foxes are sort of dying off. And so foxes die off at some rate delta. And finally, we have sort of the most interesting elementary model, which is describing the interaction between rabbits and foxes, so a predation model. And here, rabbits are getting eaten by foxes, so they die off at some rate alpha, proportional to the number of rabbits and foxes. And foxes are growing strong and healthy from eating all those rabbits, so they grow at some rate gamma, proportional to the number of rabbits and foxes. And this is according to the law of mass action. So if you look at these elementary models as sort of independent, it sort of looks like there's 2 distinct rabbit populations, one that grows and one that gets eaten by foxes. But of course, we know that in our real ecosystem, this isn't how it works. These 2 systems are both sort of pulling from the same pool of rabbits. So we can imagine we have this pool of rabbits, and these 2 systems are going to interact by exposing the populations of rabbits and connecting to that pool of rabbits. So saying these aren't 2 separate rabbit populations, they're joined. And similarly, there aren't 2 fox populations, one that eats rabbits and one that dies off. So again, we're going to expose those fox populations and connect them to this pool of foxes. So this is our first example of a compositional dynamical system. And so what is the composite? What dynamical system did we get out? So we get a single dynamical system that has both rabbits and foxes. And the way we determine the dynamics is sort of via this slogan, I call it add along shared coordinates. So for the rabbit population, we're going to add the dynamics coming from the rabbit growth model and the predation model. So we get that R dot is this guy. And similarly for foxes, add along shared coordinates. And so this really produces the Lochte-Volterra predator-prey model. So now that we sort of have this motivation for undirected composition, we now want to move to sort of what are the mathematical abstractions that describe this composition. So we're going to start off with the abstractions for composition syntax, which I think of being as like, how do we want to compose systems? So to define a composition syntax, we're going to give an operad. And in this example, the operad in question is going to be the operad underlying the symmetric monoidal category cospans of finite sets. And we're going to give this operad a name. We're going to call it UWD for undirected wiring diagrams. So we'll call it the operad of undirected wiring diagrams. And what we want to do now is sort of describe how sort of the pieces of this operad correspond to these modeling intuitions of a system interface and a diagram of systems. So the system interface is really described by the types or the objects of the operad. And so the objects of this operad UWD are just finite sets. So M is a finite set. It's a type of UWD. And we're going to draw it like a box with M exposed ports on the side. So these are sort of like M exposed ports ready to be hooked up to someone else. Our diagram of systems is going to be given by terms or morphisms in our operad. And so if I want to hook up, let's say, 3 domain types of my operad, so a box with 1 exposed port, a box with 2 exposed ports, and a box with 1 exposed port again, we're sort of thinking to the last slide. So this is going to be a morphism in UWD from 1 to 1 to, and we draw our sort of target type as an outer box. We'll say something with 2 ports. So to specify a term like this, we need to sort of wire things together. So we need a set of junctions. And then for every port, both inner and outer, we're going to wire the port to some junction. So this diagram of systems is a morphism in UWD, or a term in UWD. And you can sort of see the co-spanning nature of it. We have sort of our legs of the co-span being the inner and outer ports, and the set of junctions as being the apex of our co-span. Okay, so now we've sort of described the syntax for composition, how we want to compose systems. It's now time to turn to the semantics for composition, or like, what are the models that we're actually going to compose? So to define some composition semantics, we need to give an operad algebra over our operad. And an operad algebra is a functor. There's an operad functor. We're going to call ours dynam. This is to indicate undirectedness, and a C to indicate continuous dynamics. So an operad functor from our operad describing the syntax, UWD, into the operad underlying set with Cartesian product. Okay, so the next step is to understand how the parts of this operad algebra represent the modeling sort of intuitions of elementary models and composite model. So first, let's think about how this operad acts on types. So how does dynam act on a finite set M? So it's going to be some set, and we think of that set as being all of the elementary models that sort of fill boxes of this type. So what do we need to fill a box of this type? Whoops. We need sort of 3 things. The first thing is a finite set S, and we think of this as the finite set of states. We need some dynamics, so a vector field on the state space, RS, to its tangent space. And finally, a port map P from M to S, which assigns for every sort of exposed port some state variable to expose to the outside world. So these are our elementary models. So the last thing to think about is, how do we make composite models? And this is sort of the action of our operad algebra on terms. So suppose we have this diagram of systems. Let's see, this diagram of systems. And we're going to fill each of the sort of domain types, these inner boxes, with elementary models of the appropriate form. So for our first box, we just have one state variable, a population of rabbits, and its dynamics are grow at some rate beta. And for our port map, we're going to expose that single population of rabbits. For our middle box, we now have 2 state variables for a rabbit population and a fox population. They grow according to some dynamics, and we expose the rabbit and fox populations. And similarly for our last box. And so now we have a diagram of systems and elementary models. So how we want to compose our systems and the systems we want to compose. And so this is going to give us a model that fills our outer box. And for us, again, sort of as I shared earlier, this follows the slogan, add along shared coordinates or resources. And so in this example, we end up with 2 state variables, R and F, corresponding to rabbit and fox populations, which grow according to these rates. Oops, alpha RF, gamma RF minus delta F, and we expose the rabbit and fox populations on the ports. So this is sort of the mathematics of composing dynamical systems in an undirected manner. And so next we're going to move to, how do we actually implement that in the Julia programming language in our algebraic dynamics package. So before we begin, so we're going to start with, how do we implement syntax? And one of the sort of a common tool in the algebraic Julia ecosystem is this idea of a C-set, which I'm going to define. So given a category C, a C-set is a co-presheaf from C into set. So it's a pretty simple definition, but it turns out to be a really great tool for sort of storing data in a really domain-specific and sort of practical way. So we want to take our mathematical abstraction of this diagram of systems, this undirected wiring diagram, and produce some data structure that will help us to store that information. So we're going to define a schema for undirected wiring diagrams, and we're going to call it the theory of undirected wiring diagrams. And so let's take a look at what these undirected wiring diagrams have. So they have a set of boxes, a set of junctions, a set of inner ports, and a set of outer ports. And every port belongs to a box, and every port also needs to attach to a junction, and every outer port also needs to attach to a junction. So this is our schema for undirected wiring diagrams, and it sort of captures the information that we need to define an undirected wiring diagram. And to make this correspondence between the mathematical abstraction and the data structure concrete, we have this, let's see, proposition. Whoops, I lost the end of that sentence. Yep. Eek. We have this proposition which says that we have a one-to-one correspondence between undirected wiring diagrams, remember the terms of our operad, and finite instances of the schema. And what we mean by finite instances is we take the schema, we take the free category on the schema and look at finite C-sets over it. So C-sets that factor through fin set up here. So let's see now, let's finally look at some code and see how we will implement this in Julia. So again, we have this mathematical abstraction of the undirected wiring diagram. And so let's look at the Julia code for how to produce this undirected wiring diagram. In CATLab, there's an @relation macro, which is designed to specify what these undirected wiring diagrams are. So we specify names for our outer ports and then names for our boxes. So here we have 3 boxes: growth, predation, and decline. And we label the ports for each box. So our growth box has 1 rabbit port, our predation box has a rabbit and a fox port. And then the junctions are inferred sort of by the union of inner ports and outer ports. So just in a few lines of code, we've now created this undirected wiring diagram. And the Julia outputs 2 things. The first is a data table, or a table which sort of tracks all of the data for this undirected wiring diagram. And it also produces, where's my picture? It also, oh no. It also produces this visualization of the undirected wiring diagram. So we see our 3 boxes, 1, 2, 3, our junctions for rabbits and foxes, and we get this nice visualization of our composition syntax. All right, so I want to point out some features of implementing the syntax as a C-set. So first is that we get this nice domain-specific data structure. So undirected wiring diagrams are really specialized to this problem. But to me, even the more exciting piece is that we can now apply the features of this category C-set. One thing is that we know it's closed under finite limits and co-limits. So for example, suppose we have this diagram of systems which relates rabbits and hawks, and this diagram of systems that relates sort of rabbits and foxes, and we want to glue them together sort of along their shared rabbit piece of the diagram. So we can do this by taking a push out. So we define the diagram that's that sort of shared piece. We create morphisms that include that shared piece into each system. And we take the push out, and CATLab can do this, and it'll produce sort of the diagram, or the undirected wiring diagram that now relates rabbits, foxes, and hawks. And if you look over here in the code, we really see exactly that sort of category theory story that I just told, we define our 3 diagrams: the rabbit-fox diagram, rabbit-hawk diagram, the rabbit diagram. We define the transformations between them, and then we like very literally take the push out, and that produces this diagram for the land animals. Another feature of this category is that we can do functorial data migration, mapping from, say, C sets to D sets in a really straightforward way. So the last piece about the syntax that I'd like to discuss is this idea of hierarchical diagrams. So one of the things we can do in an operad is, is substitution, and sort of this is some idea of composition. And so suppose we wanted to create this sort of large diagram of systems that relates fishes, hawks, rabbits, and foxes, and you can imagine many more animals. And this might be hard to sort of construct right off the bat. So what we want to do is really divide and conquer and break this into smaller pieces, which we can sort of define diagrams for and glue those together. So we can define this sort of total diagram, which says we have some land system, which relates rabbits, foxes, and hawks, and we have some river system, which relates hawks and fish. And now for this land and this river system, we can define diagrams of systems that sort of fit inside of these bubbles, sort of which describe sort of the more granular view of this land and river systems. And now, so in the Julia code, we will use the O-compose method, which corresponds to substitution in our operad. And we're going to sort of compose this land diagram and this river diagram into the total diagram, and that will produce sort of this larger composition syntax that relates all the different animals. Wonderful. Okay, so we're ready to move to the implementation of semantics. So we've just been talking about how to make the diagrams that will say, how do we compose systems? And we've now produced sort of this diagram that relates fishes, hawks, rabbits, and foxes. And now we sort of want to fill them with meaning. We want to define elementary models that we actually want to compose. So just as a review, suppose we have this rabbit growth box. So we want to say, what system am I going to fill it with? Well, I need a set of states, just a single rabbit population R, some dynamics, and how we're going to expose, or what we're going to expose. So in this case, the rabbit population. So this is sort of the elementary model that's going to fit into this box. Let's take a look at how we implement that in Julia. So we have this rabbit growth model, and we have a struct called a continuous resource share, which sort of captures the data of an elementary model. So to define a continuous resource share, we need to give a set of exposed ports, a set of states, some dynamics, and a port map. And similarly for, say, this predation box, we have some states, some dynamics. We expose some of the states, and to give the code for that, we define a continuous resource share with 2 exposed ports, 2 states, some dynamics, and this port map. So these are our elementary models. So finally, we want to do the composition. So we've given our diagram of systems, which is the boxes and the wires and the junctions and the ports. We have our elementary models, which are our things that fill those boxes. And our operad algebra tells us how to compose them into sort of a single dynamical system for that outer box. So in Julia, this is really just one line of code. We can call the OApply method, which sort of does implements the operad algebra. And we're going to apply the land models and the river models, so these guys, into this diagram corresponding to the whole ecosystem. And that gives us a single model ecosystem, which now we can run through the differential equations.jl library, we can solve it and plot our results. So starting with 100 rabbits, 50 foxes, 20 hawks, and 100 fish, and running it for 10 time steps, let's see, we get this plot, and we see this oscillating behavior between the different species. So we've now sort of completed our story about how we do undirected composition in Julia, or in algebraic dynamics, and I want to give some highlights of algebraic dynamics. So the first highlight is that we can do this compositional and hierarchical model specification and analysis. So earlier we saw how we could compute this diagram of systems as the composite of smaller diagrams of systems, but we can also sort of substitute in models in this hierarchical way. So we sort of already did sort of the flattened version where we composed a bunch of independent predation, growth, decline models into a single system, but we can do it hierarchically by substituting the land models into this land diagram to produce sort of a single model corresponding to the land system. Similarly, substitute the river models into this diagram to get a single model corresponding to the river system. And then we can apply those two now single models that we can, test and do analysis on into our total diagram to produce our ecosystem. And the applied category theory, the mathematics of this tells us that these two systems are identical in their behavior. Yeah, and we can also do compositional and hierarchical model analysis. So if we want to do some analysis such as Euler's method or fixed point analysis, we can do that analysis on subsystems, so either in the individual boxes or perhaps on the land system or on the river system, and glue those analyses together into an analysis of the total system. Okay, so sort of going back to our main idea, we've now really zoomed in on each of these each of the boxes in our table for undirected composition. We've discussed the modeling terminology, the Operad and Operad algebra, and the Julia implementation in algebraic dynamics. So next, what we're going to do is take a different flavor of composition called directed composition and sort of tell the same story, but we're going to go really zoom through it. But we'll pause a few times to sort of point out some highlights of algebraic dynamics. So to give some motivation and some intuition for directed composition, this is really inspired by the Operad algebra of continuous dynamical systems defined in a paper by Wagner, Spivak, and Lerman in 2015. And we really implemented just like a very small generalization of that. So the idea is we might have these subsystems that correspond to some rabbit population and some fox population, which receive some input to sort of do their dynamics and give some output. And then they compose by sending information to each other along these wires to again produce the Lochte-Volterra model. And the generalization from the algebra described in this paper is that we're going to allow the merging and the creation of wires. So to give a flavor sort of the Operad and the Operad algebras corresponding to the syntax and the semantics for directed composition, I know there's a lot on the screen, but we'll step through it. So for the composition syntax, we need to give an operad, which we're going to call DWD for directed wiring diagrams. And the types of that operad are pairs of finite sets, which correspond to a finite set of incoming ports, a finite set of outgoing ports. And the terms of this operad are these directed wiring diagrams, where we sort of wire between ports. For our composition semantics, we need to give an operad algebra. Again, we're going to call it dynam, but this time we have an arrow to indicate directedness, the C again to indicate continuous dynamics. So the action of this operad algebra on types gives us our elementary models, how we can fill boxes of this type. And again, we need three things: a finite set of states, a vector field, or parameterized dynamics, so a vector field from the state space and the input space to the tangent space, and finally a readout map. And now the action of the Operad algebra on terms tells us how to compose models, and it follows the slogan, send information along wires. So this is sort of the mathematics of directed composition. You can read about it in more detail in our paper. And now sort of to move on to the implementation side. So again, the first thing we want to do is to represent our diagram of systems, or the terms of our operad, which look like these. And so again, we're going to give a schema called the theory of directed wiring diagrams. And we have this proposition that we have a one-to-one correspondence between the mathematics of the directed wiring diagrams, the terms of our operad, and on the right-hand side, finite instances of this schema. And then let's take a quick look at the Julia code. So here we're sort of switching up our diagram. We're going to look at this diagram of systems that corresponds to the multi-city SIR model. So we're thinking about people in city 1, city 2, city 3, and people flowing from city 1 to city 2, city 2 to city 3. And if we look at the Julia code, I actually want to pause because we see here, we specify the number of cities, the roads between the cities, so city 1 to city 2, city 2 to city 3. And then we've written a method which takes the number of cities and the roads and produces the correct wiring diagram. And the thing I want to highlight is that not only is algebraic dynamics a domain-specific language for compositional dynamics, but you still get all of the power of Julia behind it. So you can still, write for loops and conditionals and all that good stuff to produce the wiring diagrams that we want. And just as in the undirected case, CATLab will produce a visualization of our diagram of systems for us. So over here, this is produced by CATLab. All right, so that is the implementation of the syntax. And for the implementation of the semantics, again, we have our diagram of systems. And in the mathematics, we need to define sort of what are the elementary models that can fill these boxes. And in algebraic dynamics, in the Julia code, we have continuous machines are now the struct that represent the elementary models. And to produce a continuous machine, we need a set of inputs, a set of states, a set of outputs, some dynamics, and a readout map. All right, so finally, we're ready we've made our diagram of systems, we've made our elementary models, we're now ready to do the composition. So we have this diagram of systems, which again sends people from city 1 to city 2 to city 3. And we have our elementary models. So we're filling each city with a single city SIR model. Corresponding, we have a susceptible, infected, and recovered population for each city. And now we're going to glue them together by sending the information along the wires. And we now get a multi-city SIR model which contains those susceptible, infected, and recovered populations for each city. So again, in the Julia code, we can do this sort of composition in a single line of code. We want to apply the city models to this city diagram, and we get out of that the complete multi-city SIR model, which we can now solve and plot. So if we start with 100 people in each city, and a single infected person in city 1. If we plot just the infected populations for each city, we see that the infected population for city 1 peaks first, followed by peaks in the infected populations for cities 2 and 3. Okay, so that was sort of a whirlwind tour of both the mathematical abstraction and the implementation of directed composition of dynamical systems. And in our last few minutes, what I'd like to do is sort of point out another highlight of algebraic dynamics that sort of goes with this example. And so that highlight is the idea of that we have independence between model syntax and model semantics. So for example, suppose we want to see what the effect of having different roads between cities are. So we have our original, where we have people moving from city 1 to city 2 to city 3. We can imagine this other model where we have people moving from city 1 to city 2 and city 2 back into city 1, leaving city 3 as this isolated island. And finally, we could have this third diagram where we have people flowing from city 1 directly into cities 2 and 3. And now we're going to use the exact same elementary models. So we're keeping the model semantics intact, and we're going to fill each of these patterns with the same SIR models for each city. And we can see the effect that that has on these plots of the infected populations. So in this middle example, we see that city 3 is an isolated island. So even though it has the same dynamics as in this example, it never receives any infected people. So the infected population stays 0 the whole time. In our third example, we see that the infected population of city 3 peaks earlier than it does in the first example, because it's receiving people directly from city 1 instead of sort of mediated by city 2 in this case. So this is an example of sort of changing the model syntax while leaving the model semantics intact. But we can also do the opposite. So we could leave the model syntax the same and change the model semantics. So an example of this is like, suppose you wanted to investigate the effect of quarantining on this epidemiology model. So we're going to leave the syntax of this diagram of systems intact, people flowing from city 1 to city 2 to city 3. But now we're going to change the internal models by adding a quarantining population to each city. And so in the Julia code, that corresponds to changing the city models and sort of what are the continuous machines that we're going to define that will fill each of these boxes. And so again, we're going to apply these new models to our original city pattern that looks like this. And when we plot the results, we see that quarantining has a big effect on the infected population. So we have the peaks of the infected populations in the cities are much lower in the SIRQ model than in the SIR model.
You have 5 minutes left for both talking and questions. Thank you.
Thank you. All right. So we've now sort of completed our sort of tour of that table of those three worlds. And I want to conclude by sharing some of the contributions in our paper that maybe we didn't get a chance to discuss today. So I first want to start with this left-hand side, which sort of describes the mathematical abstractions that are really highlighted in our paper. So for undirected composition, directed composition, we define these operads of undirected wiring diagrams and directed wiring diagrams. Today, we discuss these algebras of continuous systems, but in the paper, we also examine these algebras of discrete systems and this Euler's method, which is a natural transformation between them. And so one of the main contributions is implementing sort of all of these pieces, the operads and the algebras in Julia in this package algebraic dynamics. We also give sort of, some of these are also new algebras for composing dynamical systems, often extensions of previous work. And lastly, we also have functorial Euler's method. So both proving that these are indeed natural transformations and also implementing them in algebraic dynamics. And the last contribution that I want to zoom in on is often we think of like mathematicians describe abstractions and then, then we implement them. But there's really sort of a two-way street here where sometimes implementations can inform abstractions. So we've defined a new operad of circular port graphs, which is a sub-operad of directed wiring diagrams. And this really came out of implementing things like the finite difference method and cellular automata. And so I think this is a great example of this like connection between finding abstractions and implementing abstractions. And so some of the future work that we're really excited about is this idea of not just implementation informed by abstractions, but also abstractions informed by implementation. We're also interested in implementing abstractions coming from higher category theory in this realm of compositional dynamical systems. And lastly, we saw that we had these operads, which sort of, we described the terms as C-sets, and we're interested in a general theory of these types of operads. So thank you so much. I'd like to thank, this is sort of this summer's Algebraic Julia team. You can learn more about Algebraic Julia and all of its wonderful packages here and some references. So thank you.
Thank you, Sophie, for an excellent talk. Very interesting. Are there questions? And Jamie, can you help me with knowing what's happening in Cambridge? And for the online audience, maybe if you raise your hand.
So we do have a question here, if that's all right, Dorette.
Start with Cambridge, then we'll have some online ones.
Hi. So you're clearly using explicit category theory in the formulation of the models in the code. You were sort of hinting about this at the end. Are you currently using completely classical methods to solve the models, like just hitting it with the built-in ODE solver of Julia? Or are you able to, or working on like exploiting the decomposition that you have in the numerics?
Right now, we just sort of hit it with these explicit solvers that are already implemented. But the second thing that you said is exactly like some future work that I'm really excited about, is how to improve that solving by using the compositional structure.
Okay, thanks.
Thank you. Marcelo, you can unmute yourself.
Yeah. So thanks for the talk. Really interesting. I would like to ask you if you have considered a situation like, for example, people that are moving from one city to another with different velocities. So when you have like, I don't know, maybe weights on the morphisms, did you try to do something?
Yeah, so when you implement the model sort of semantics, you can encode some of those things like rates in that, yeah. And
Okay.
that's something that's neat about you really have a lot of freedom in how you define these dynamics.
Okay, and if I can, is there a relation with coloring the operads, or it isn't?
Oh yeah, so sorry, I should have said at the beginning, but all of the operads I discussed today are really colored operads, where
Okay.
the different types correspond to the different colors.
Okay, thanks so much.
There is a question in the chat that's just saying, isn't weight implicit in the models? And I guess that's probably correct, Sophie.
Yeah. Or you define them when you define the models. Yeah.
Any questions from Cambridge left?
Yeah, we've got one more question here in the audience.
Okay.
So when you had the roads coming from one city to 2 and 3, going like that, why didn't the infections arrive at 2 and 3 at the same time?
Great question. They have different infection rates. So if you look at, not here. Oh no. If we zoom in on the parameters, we see that the infection rate in city 3 is lower than in city 2.
Great, thanks.
Yeah.
Okay, let's then all unmute and thank Sophie for an interesting talk.
Okay.
Okay, our next speaker is John Foley. And could you share your screen? Okay. So our next speaker is John Foley from Metron Incorporated, and he will speak to us on Operads for complex system design, specification, analysis, and synthesis. Thank you, John.
Thank you. I'm just going to set a timer for myself to keep myself on track. Okay, so yes, this is going to give you a quick overview of a review that's with Spencer and Sub from NIST and a colleague, John Dusel at Metron. So the paper is centered around 3 applications that motivate how typed operads, also known as colored operads, as we've been discussing in the last talk, it address some issues for complex system design, namely specification, analysis, and synthesis. And so I guess we were just seeing how some models could be synthesized in the context of dynamics. So that's all very interesting. And so these are all motivated by 3 domain problems. Just to give you a quick flavor of these, the first is a maritime search and rescue domain where types of assets are put on other assets to build an effective architecture for search. The analysis is from a precision measurement system at NIST, describing the analysis of that particular system. And then there's a synthesis is actually for tasking the behavior of SAR on land that was, the specifics of the problem were inspired by recent wildfires this past fall in California. Okay, so typed operads, this is a paper for a general scientific audience, and so really we were trying to emphasize that anytime you have n objects being composed into a single object, typed operads kind of naturally arise. And the analogy that I'll step through here that is maybe salient and makes these objects a little more friendly is that the types or for an API, an application interface, are analogous to data types, whereas you have abstract methods that correspond to operations or the terms, as what the term was used in the last talk. Composites are writing scripts from methods, And then algebras actually describe how you implement methods. And so just as we saw before, type operad has these types, operations that are composed, and some ways of making permutations of arguments coherent. But really the point here is just that this is something, as long as you have many in and many out, it's a very natural thing that comes up in lots of contexts, as we saw in the last talk in the context of dynamics. Okay, so let's jump into this specification example. So first of all, sort of the moral here that we're trying to espouse is that specification becomes practical when you can provide simple combinatorial ingredients for functorial semantics. So that's exactly what we saw in the last talk, right? You gave ingredients for what your syntax was, what your semantics were, and you were able to come up with these nice functorial models. And so here, what I'm talking about, we're going to emphasize just the syntax only. But the example we do in the paper is using the tool network models, which allows you to describe syntax for how you compose a specific kind of network by describing how those networks are overlaid or put side by side. So the canonical example of this, you have simple graphs, which you can overlay by taking edge union, as we see here, or you can put a simple graph side by side by taking their disjoint union. And so a network model is this machine that gives you a network operad. And so if you have the types for your particular application, the sort of types of atomic nodes that you're interested in, use that to form the set C. To encode how you overlay and put networks side by side, you encode that with a symmetric monoidal functor, where overlay corresponds to composition of the target categories of this functor. And this side-by-side operation is actually the lax structural map. When you hit one of these monoidal functors with the monoidal growth engine construction, you actually get a full-blown monoidal category, where the lax structure maps are actually how you're defining what your tensor is in that category. And then there's a canonical structure, a canonical construction of an operad, where you just consider the multiple inputs to be generated by tensor products. And so this is a tool that lets you take sort of build syntax from scratch, right? This is a particular tool to do that. And so how do you actually try to use that in practice? Well, you want even simpler ingredients, right? As we sort of like in the last talk, that will tell you how to build the syntax. So for instance, if you codify in a theorem, this is one example where for each monoid, you can associate functorially a network model, which would then give you a network operad for syntax. Once you have a theorem like that, you sort of have a recipe to build syntax. And where this comes up in our particular application area, it's not exactly the same theorem, but similar. You specify the atomic types for the SAR domain, which is a laundry list of 8 atomic types, which includes here the green cutter, the red helicopter, and this blue quadricopter. And then you need to describe the family of monoids that you're going to use to construct your network models, which just describe which types are the right size to be put on other types. And so all this data can be specified in a, looks like my colleagues are trying to talk to me. So all this data can be specified in a, a simple data structure. For instance, here we have this in JSON, which would then say, all right, so we have the monoids, which tell you the network model, which tell you the network operad. And that's sort of the machine that we use to give an example from simple ingredients. Okay, so let's move on to analysis. So the slogan for this is compositionality guarantees coherent analysis. So you can do not just sort of one ad hoc analysis, but you can do multiple complementary analyses. And so for this example, the wiring diagram is actually just an ordinary commutative diagram, right? Sort of, but instead of a commutative diagram in arrows, it's a commutative diagram in operads, typed operads. And so here, right, if you go along one side of the diagram, you get a decomposition of your system in terms of function, where you first compose these length systems and temperature systems, and then those are combined to form the whole length scale interferometer. Or you could do this decomposition by control, which would be the other side of this diagram, where you're going grouping things by actuators and sensors. And the nice thing about these perspectives is, though the syntax that you're using covers both of these ways of looking at your system, right? You can also use different semantics for these different aspects of your problem. And so what's described here very briefly is, from the functional perspective, you can describe how component failures bubble up into the system as a whole. So in this case, your semantics are describing relative probabilities of multiplication. So they're given here for the various morphisms, and then you know how they contribute to failure probabilities. If you were going to analyze control, on the other hand, you would be interested in dynamics, as in the last talk. And so in this situation, it's a little more complicated, but for instance, there's this laser interaction, which is coupling some components, and it's parameterized by the temperature, relative humidity, and pressure of the laser, which are dynamic, that vary in time, and then this constant in time laser wavelength. And together, those are giving you these trajectories, which are describing what the interaction between the systems that are managed by the laser are. And then if you keep going and you describe all the possible behaviors for joint interactions and the individual component states, you actually get a semantics for these dynamics in the category of relations. And this is following, the usual sort of thing in the Wellham's behavioral approach, right? Where you're saying sort of the possible behaviors of the system. Okay, so what are we trying to emphasize here with this analysis example? First of all, we're limiting the focus here, which is done using the syntax. So I was just telling you about only sort of a small fragment of this operative port graphs, this sort of commutative diagram, the category that you get associated to that commutative diagram, and well, not the category, the operad associated to that commutative diagram. But what this means is that you only are having to define semantics for the problem at hand, which is exactly what happened in the Julia programming language, right? You were only sort of describing what specific things you were putting in the boxes, but what we can also do, if we wanted a more granular analysis, you could also extend what this category is, the sort of this sub part of the operad that you're working over. So that's sort of an important moral that I think is important for application. And then finally, each model, or not finally, but additionally, each model leverages a specific filter. And so we saw these two different filters. And if you want to get more into this in the paper, they also talk briefly about using filters of filters, which are natural transformations, like this idea we saw earlier, where you were switching from continuous to a specific type of discrete dynamics. It's definitely that sort of idea. Okay, well, finally, let's get through a little bit of a synthesis. I'll try to slow down maybe a little bit here, but we're still very pressed for time. So in theory, synthesis should be straightforward if you have sort of simple objects and morphisms or operations that generate your syntax, right? So if you have basic building blocks, you should be able to put them together. Okay, so what could give you that kind of data? Well, here we're dealing with a tasking domain where we're just considering this red refueler and an orange refueler and a red rescuer here. And so a Petri net will describe how primitive tasks fit together. And you have transitions, which are declaring the primitive task. You have arcs, which are indicating the atomic types involved in each task. And here, actually, the species are representing coordination locations. So for example, this tau 3 is an example of a refueling operation where the refueler refuels the refuelee. But in order to do that, they both need to rendezvous at this location C, so that that will actually be. And so these are discrete coordination locations, which are only giving physical location semantically. Okay, and so these sort of tools are known to sort of be sufficient for these kinds of problems. They generate monoidal categories. So what is this going to look like in terms of all the tool set? Well, the idea is we're using this Petri net here as a specification language. So if you want to specify a syntax for tasking systems, you're actually going to use a Petri net. And so, well, that means we need to get a network model if we're using network models to construct them, which will give us a network operand and so on. And so the way a Petri net does this is the token colors, which also correspond to the atomic agent types, will give you C. In order to make this work with respect to these symmetries, you do want to have, as in this last example, the transitions preserving the number of tokens. And then what these target categories actually do is they describe the allowed behaviors for each a simple set of agents. I'll give a couple examples of that in a moment. But then when you do this, you construct a network model, and then that gives you an operand for syntax. Okay, so what does that actually look like? Well, for instance, if you have this orange refueler, if you only have one of those, it actually can't do anything except stay in one place, because there's no transition that it can do by itself. For this single rescuer, you have a couple things that it can do by itself. But actually, for safety reasons, over here, it has to operate in pairs in order to proceed to D. So it can't actually do that. And so that's giving you a subset of this category generated by the transitions. Now, if you assemble two of these together, right, well, you could either do independent behaviors where this does nothing, and then the rescuer does something, or you could do this new joint behavior that involves both of them. And that's sort of how these categories are built up, and then if you stratify these, then you get, you know, your symmetric monoidal category, and if you wish, a typed operand. And that's sort of how the construction goes. So what do we actually do with this? Well, we tried to prototype synthesis, and so we were able to do this with a constraint program. And in the realm of Petri nets, this is based on this is similar to constructions that have been done in the past. The main thing that's a little more interesting, we also extended this to incorporate semantics, where we had state variables that were corresponding to those. But the dictionary that you use for this sort of thing is you turn your types into Boolean vectors, and then these primitive morphisms, which parallel composition of primitive morphisms correspond to these Boolean vectors indexed over transitions, and then the relationship between targets and the sources of morphisms is described by an equation, which depends on the primitive morphisms involved, and then to match sources to targets, so which is the requirement to compose morphisms, you have this constraint where there's an inequality that allows for identity morphisms. So identity morphisms would not be showing up as variables in terms of your primitive morphism. So anyways, you put this stuff together and you get a constraint program, but of course, it's a very complex problem. And so this is not going to be an effective way to do this in practice, right? That you will be able to get something that you can compute with, but you're not going to be able to push it very far. And so sort of what I just went over were these three examples, which are these three different threads. And sort of the perspective we take in this paper, and which I'm offering today, is that you really need to weave these threads together in order to get an effective system, right? The fact that you can sort of specify basic building blocks and use that to analyze things, really that's put together. Those work together thanks to the principle of compositionality, right? Since you can build the whole up from the parts and how they're put together, that allows those to work together. Likewise, generators are sort of you want some sort of generated information to deal, to make synthesis work. And finally, what the piece that's really missing here in making this automatic synthesis work is using the sort of analytic power of compositional mathematics to actually make the problem more scalable. So I guess I believe Jules who kind of hit it on this, like, are you actually using how this is broken down, to make your dynamics more scalable? And so that's something for future work. And we actually describe lots of different directions for future work in this paper. For instance, we do describe methods for semantics, but they could be made more systematic. This is sort of similar in flavor to this question of what are the operads that correspond to these co-presheaves or that sort of thing. How do you sort of make this systematic? And what are more examples of sort of focused analysis of complex systems? We have this nice example from my collaborators. Is there really a good way to unify the analytic and synthetic perspectives? So this network operad way of thinking about things is very combinatorial, very bottom up, but typically the way you think about wiring diagrams can be top down. Now, of course, if you're defining all the boxes and putting them together, this can be synthetic, as we saw before, but really it's, what's this good way to unify these two perspectives?
Minutes left, including questions.
Okay, so this is my last slide. Okay, so, and then finally, there's this question of, can you exploit multiple representations? So this really goes back to Eilenberg and McLean. Do we really need category theory if we're not using natural transformations, right? And so this little doodle that you have before you is maybe something that looks like where you have linked specifications that are giving you maps between sort of this core meta model, and then you may actually need exploitation libraries that use specific of various domain problems to actually sort of operate over those as fast as you possibly can. But all this mess is sort of kept together. All this scruffiness is kept together by making sure you have this core reference model. So anyway, check out the paper for more discussion. Thank you for this opportunity to speak. Here are some papers that you can check out if you are interested in this stuff. Thank you.
Thank you, John. And we'll take a minute or so for questions. Are there questions either in Cambridge or in here online? If there are none, then maybe we can take time later during the breaks to talk further with John. So let's thank John by unmuting ourselves. And our next speaker will be JS. And John, if you stop sharing, then JS can share. Okay.
How's that?
That looks good.
Awesome.
Thank you, JS. And so JS has just moved to Mount Allison, I guess. Is that official? And will speak to us today on Jacobians and gradients for Cartesian differential categories.
All right, thanks. So this is going to be a bit, I guess, of a different flavor from the other talks so far. I'm sure some of you might even think that this isn't applied or doesn't belong at the ACT conference. But hopefully what I'll do today is instead introduce some tools that other people in the future might use for applications, or that I'm hoping that will be useful for applications in the future. So, so as in the title, today's talk is all about these Cartesian differential categories, which I'll just call CDCs. And essentially a CDC comes equipped with a differential combinator D that formalizes the directional derivative from multivariable calculus. And these are introduced by Blue-Cock and Seeley. So the idea here is that for any map from A to B, the differential combinator is going to produce its derivative from A cross A to B, called D of F. And the main example that you should keep in mind is the category of Euclidean spaces and smooth functions between them, where the differential combinator gives you precisely the classical derivative from calculus. And an important class of examples of CDCs are the Cartesian closed differential categories. And these are the ones that provide the categorical semantics of Erhard and Renier's differential lambda calculus. And there are lots of other interesting examples of CDCs out there in the literature. But the cool thing is that CDCs and their variants have found numerous applications in computer science recently. So for example, you have work in causal computation by Sprunger and Katsamada. You have work in incremental computation by Alvarez, Picalo, and Ong. Game theory by Lard, Manzanero, and McCusker. And differentiable programming by the work of Abadi, Plotkin, Crotwell, Gallagher, and Prunk. And probably the coolest thing and the most recent thing is applications of CDCs to machine learning with the recent introduction of these things called Cartesian reverse differential categories, which have been shown to be a suitable setting for reverse gradient descent. And I believe someone in tomorrow will talk more about this. But as my title suggests, I'm going to want to focus in on important concepts in differential calculus, specifically the Jacobian matrix and gradients. And these are fundamental tools both in differential calculus, but also in automatic differentiation and machine learning algorithms. The problem is that Jacobians and gradients have yet to be formally defined in a CDC. And the need for these to be expressed is expressed by Katsamada and Sprunger in their conclusion, where essentially they say, look, we've done this cool construction, but we can't actually do machine learning yet because we don't know how to do Jacobians and gradients inside a CDC. So the goal of today's story is to give you how to do Jacobians and gradients in the context of a CDC. So just so we're on the same page, let me just recap what Jacobians and gradients are. So remember that for a smooth functions from Rn to Rm, which is actually a tuple of small smooth functions Fi's from Rn to R, just to R, the Jacobian matrix is going to be a matrix of size n by m, whose coordinates are the partial derivatives of the little Fi's. And because the Jacobian is a matrix, then there's an associated R linear function to it. And when you apply the Jacobian matrix at X evaluated at some vector Y, then what you obtain is the derivative of the smooth function, capital F. So from this point of view, the Jacobian can be interpreted as a map from Rn to the vector space of linear functions between Rn and Rm. And for those of you with a bit of background in analysis, this is how the Jacobian is a special case of both the Fréchet derivative and the Gatto derivative. Now for a smooth function, just from Rn to R, the gradient is just defined as the Jacobian, as the transpose of the Jacobian. And so from that point of view, the gradient of a function is now seen as a map from Rn to the linear maps from R to Rn. So you see the codomain is now in the domain part, and the domain is now in the codomain part. So there seems to be some sort of currying and closed structure going on here. So, as suggested by Katsamada and Sprunger, one's first attempt might actually be to consider the Cartesian closed setting. And this is a good idea because this would capture models of the differential lambda calculus, and you'd actually get reasonably far in just defining the Jacobian and working out the basic properties and so on. But there's a crucial flaw. Unfortunately, this approach would exclude numerous examples of CDCs, specifically those with a finite dimensional flavor. So for example, the canonical example of a CDC, the category of smooth functions, is not Cartesian closed. So another approach is required. Now, remember that a few slides ago, I mentioned that the codomain of the Jacobian can be interpreted as the linear maps from Rn to Rm. And as a vector space, this is isomorphic to R to the nm. So from that point of view, it can be seen as an object in my category of smooth functions. So while the category of smooth functions is not Cartesian closed, there is a sensible notion of internal linear Homs. And this is the key concept that makes this whole story work. And what's cool is that someone recently pointed out to me that internal linear Homs have actually been used by Vakar in his recent work on automatic differentiation and linear logic. And the even cooler thing, and the whole thing that makes this work, is that there is a canonical notion of linearity inside any CDC, which is linked to the differential combinator. So here's a sort of the summary of today of the results in my paper. The main definition that I introduced was this notion of a linearly closed Cartesian differential category, which is a CDC with these internal linear Homs, and where I'm able to curry maps with linear arguments. And then the Jacobian is going to be defined just as the curry of the derivative of f. And to define gradients, well, I also need this extra notion of having a transpose, because I'll define the gradient as the transpose of the Jacobian. And so hopefully, I've already shared these ideas with the people in those application slides, and they seem very interested. I'm hoping that these formal notions of Jacobians and gradients will be particularly useful when we actually sit down and generalize and formalize and even apply these automatic differentiation and machine learning algorithms inside of a CDC or CRDC. So at this point, if you're already bored, I only want you to take away this slide. And now I'm going to get into some technical details. Of course, because of time, I can't go into the full details. Please see the paper for all the nitty-gritty stuff. So let me briefly just introduce you the formal definition of a CDC. So a CDC is a category with finite products, such that every Hom set is going to be a commutative monoid. So that means that I can add maps together, and I have zero maps. But only precomposition is going to preserve the additive structure in the sense that these equalities hold. Now, those of you familiar with the enriched category theory may be wondering, well, what about the other side? Well, for a Cartesian differential category, we don't want that because, for example, while we can add polynomials together, there are some polynomials like x squared which don't preserve addition. So we're only really asking to be able to add maps together and not that every map preserves addition. A CDC also comes equipped with a differential combinator, which explicitly is a family of operators of this type, which for every map f spits out d of f now of type a cross a to b. And d of f is called the derivative of f. And this satisfies 7 axioms, which captures the basics of the derivative from differential calculus. So this includes the chain rule, additivity in the second argument, symmetry of the partial derivatives, etc. And to help us out in some of the slides, I'm going to use sort of this term logic element-based notation for CDCs. So I'll write my derivative like this. And those that are curious, there is a sound and complete term logic for CDCs, and it's quite useful when you're doing some technical proofs. So as I mentioned before, the canonical example is the category smooth, whose objects are Euclidean spaces and whose maps are real smooth functions between them. And the way you explicitly define the differential combinator is that for a smooth function from Rn to Rm, its derivative d of f, now of type Rn cross Rn to Rm, is going to be defined as the Jacobian matrix of f evaluated in the first argument x, multiplied by the second argument y, seen as a column vector. So when you work that out, you obtain a column vector whose coordinates are the sums of the partial derivatives. In the special case where m, the codomain, is equal to 1, then what you obtain is precisely the directional derivative of f at point x along the vector y. As I've mentioned, there's an important class of maps in a CDC, and these are the linear maps. And these are maps which are linear in certain arguments. And a linear map is essentially, a map is linear in an argument if when I differentiate with respect to that argument, while I keep the others constant, one gets essentially back the starting map. So explicitly, a map is linear if when I take its derivative, I just obtain back f, evaluated at the second argument b here. And I can also define what it means for a map to be linear in its second argument, which essentially means that it's linear with respect to the partial derivative. So just like in classical calculus, partial differentiation is obtained when I evaluate some arguments at 0. And then something is bilinear if it's linear in each of its arguments separately. Or we can explicitly write out what that means. So a map is bilinear if its derivative is equal to this. Linear maps form a subcategory, which I'll define as lin of x. Now, one of the axioms of the differential combinator tells us that for any map f, its derivative will always be linear in its second argument. And this is captured by the fact that d of f in the smooth example is defined by matrix multiplication. Now, the cool thing is that maybe even if you don't understand this notion of linearity from a Cartesian different point of view, I really only need you to understand it in the example of smooth, where being linear in the CDC sense is the same thing as being linear in the classical linear algebra sense. So what that means is that a smooth function is linear in the CDC sense if and only if it is R linear, so it satisfies this equality. So lin of smooth is the category of vector spaces of the form Rn and R linear maps between them. So now, with all this set, I can now introduce the main definition of my paper, which is a linearly closed Cartesian differential category, which is a CDC such that for every objects A and B, there is an object L of LAB called the internal linear Hom. There's a bilinear map from LAB cross A to B called the evaluation map. And for every map F of type A cross B to C, which is linear in its second argument, there is a unique map called lambda of F, which I'll write in the term logic as follows, called the linear of Curie of F, such that the classical well-known Cartesian triangle of in a Cartesian closed differential Cartesian closed category holds. But again, it's super important to note that this is not the same as being Cartesian closed because I can only Curie maps which are linear in their second argument. Also, the internal linear Homs interpret the internal version of the linear maps from A to B. And I'd also like to stress that this does not mean that the subcategory of linear maps is Cartesian closed. However, there is a notion of a CDC having a linear tensor product, and this is studied by Blue, Cocken, and Seeley. And I conjecture, and I think it's like a one-step proof, that this is equivalent, that being linearly closed in the setting of having a linear tensor product is equivalent to the subcategory of linear maps being monoidal closed. And this approach was studied by Gallagher and McAdam independently. In a linear CDC, I can define the notion of Jacobians. So the Jacobian of a map F from A to B is going to be the map JF from A to L of AB, defined just as the linear Curie of the derivative of F. So JF is equal to lambda of D of F. And I've written it out here in the term logic. So in my main example of smooth, smooth is a linearly closed CDC. The internal linear Hom between Rn and Rm is R to the Nm. In the evaluation map, well, what it does is that in its first argument, it's going to have it's going to input a vector of size n times m, and it's going to lay it out as a matrix. And it's going to multiply that matrix out by the second vector, which is now only of size n, and you obtain a vector of size m. And the cool thing is that when you have m equals 1, then this evaluation map gives you back the dot product of vectors. Now for a smooth function, it turns out that the Jacobian in the CDC sense is just the Jacobian matrix laid out as a column vector. And you reobtain the Jacobian matrix when you input it into the evaluation map. All right, so now the next thing is we also need to talk about how to define gradients. So remember that I mentioned that the gradient is equal to the transpose of the Jacobian. So we can also define the notion of having a linear transpose for a linearly closed CDC. And this is a linear map. This is a family of linear maps for every objects A and B of type LAB to LBA. So it swaps the A's and the B's, such that this transpose status captures the classical identities that one would expect from matrix transpose. So this includes the fact that the transpose is idempotent, that it swaps the order of composition, that it preserves identities, etc. And then the gradient of a map from A to B is going to be the map A lambda is going to be lambda f, now of type A to LB of A. So the codomain of f now appears in the domain part of the linear Hom, and it's just defined by postcomposing the Jacobian of f by the transpose. So in other words, the transpose of the Jacobian. Now, as I've mentioned, what's neat about this is that this notion of having a linear transpose is closely related to this idea of Cartesian reverse differential categories. So I won't go over the definition here because someone's going to talk about it tomorrow, but essentially a Cartesian reverse differential category comes equipped with a combinator R this time, which for every map from A to B, you obtain a map from A cross B to A. So again, this idea of the codomain part now appearing in the domain for the reverse derivative. And then we obtain a really cool result, which is that a linearly closed CDC with a linear transpose is precisely a linearly closed Cartesian reverse differential category. And in this case, you would have... Sorry, I hear some keyboard. All right.
You have 1 minute left, by the way.
Yeah. So in that case, the gradient is defined. The gradient is then obtained just by taking the linear curry of the reverse derivative. So our favorite example, smooth, is a linearly closed CDC with a linear transpose, and therefore a linearly closed Cartesian reverse differential category. Just very briefly, while not every linearly closed CDC is going to be Cartesian closed, we can precisely tell you when a Cartesian closed CDC is going to be linearly closed. And essentially, it's when a canonical linear idempotent splits. And then you can take the linear idempotent completion of any Cartesian closed differential category to obtain a linearly closed Cartesian closed differential category. So if you're interested in that, there's more details about that in my paper. So just wrapping up, just some final ideas. I conjecture that it's possible to give an alternative axiomatization of linearly closed CDCs completely in terms of L, the evaluation map, and J, where the differential combinator would be just defined as the evaluation of J. And similarly, we can do the same story for Cartesian reverse differential categories, but where this time we can axiomatize them completely in terms of L, the evaluation map, lambda, and the transpose, where the reverse differential is just R, going to define as the evaluation of lambda. And then because now that we have obtained Jacobians and gradients, well, it should be straightforward to do other cool things from calculus that we all seen in first year university, like the divergence, the curl, the Laplacian, or the Hessian, etc. And that's it. Hope you enjoyed my talk. Thanks for listening, and merci.
Thank you, JS. A nice talk. Are there questions either in Cambridge or here on the online audience?
So I have a question here in Cambridge. So JS, when we work with Jacobians, we're very often interested in the determinant of the Jacobian as a matrix when it's square. Can you say anything about determinants from your picture?
Yeah, so I think that the determinant, the way you would obtain the determinants is probably better captured when you have this this linear tensor product, and then you could and then if you also assume that your category of linear maps, I think, has cups and caps, then you can capture the determinant using cups and caps. But I haven't looked much into that, but I do think that it's possible.
I'm not familiar with exactly what you're referring to there. Maybe you could tell me another time.
Sure.
Are there other questions? If you're online, please use the raise hand function or unmute yourself.
So we have another question here in the lecture theatre.
Go ahead.
Nick is racing at high speed.
I can't hear anything.
Can we get that louder?
So on this slide, you say that when a CDC is a linear tensor representation, then you have this conjecture about it being linear closed if the linear subcategory is monoidal closed.
That's right.
But, you know, if you don't have a tensor, is being linearly closed equivalent to lin X being closed, non-monoidal closed, in the sense of having HOMs, but not?
Oh, I see. The short answer is no, because in the definition of closed, you also assume a unit. But it would be one of these non-unital closed examples.
Right, yeah. The pro-unital closed categories of, yeah, Schulman.
Yeah.
Thanks.
Any other questions? If not, then let's thank JS by unmuting and clapping. And I guess it's time for tea in Cambridge. And after that, the adjoint school in a half-hour time.
Hello.
Hi.
Direct.
Hi, David. Good to see you.
It's good to see you too. How have you been?
Good. Just been a couple of crazy months, but
Well, it's good to hear that you're doing well. So is this tea time?
yeah, until what would be 12 noon for us. So yes. 4 o'clock, I guess, for you guys.
I'm in California now, so it's
Okay, so we okay, 4 hours instead. So 8 o'clock in the morning.
yeah.
So you didn't actually go down to Cambridge either.
No, I went the other way. Yeah.
So but you are involved. So are you guys doing the school online as well? Then?
We did it online, but group 1 was mostly in Topos, or like a large. They had 6 people, and I think 4 of them were in the Topos Institute here.
Nice.
So that was
nice to be.
yeah. So they got a little bit of the in-person action, but no, most of them were working literally around the clock. And keeping very strange schedules the past week. So, do you know who I talked to be made a co-host or to set up?
Let me see whether I have those powers. I think I don't anymore. No, I think ACT Cambridge needs to come back in.
Okay, then there's no rush. I've missed the entire conference.
Jamie did it for me earlier, so that's
great.
So David, are you finished with the school after this week, or are you?
Yes, this is the end of the school for this year, and then yeah. But I think Sophie and I will stay on as organizers for next year, so
Nice.
we'll be around.
Is this the Adjoint school?
Yes. Okay. Yes.
I really wanted to participate in that, but it actually it completely slipped my mind, and only got on the ball with it when I was submitting my paper here to ACT. So yeah, maybe I'll check it out next year and see if there's an opportunity there. How was it? Was it?
Please do.
What is do you think? I mean, will you be talking in the next session now?
The next session is going to be the sort of a bunch of work in progress presentations of what the students did during their research week. But we'll only have, I think Brendan will be here to give a short introduction to like what the school is.
Okay.
But the basic idea of it is that we have an online reading course where we meet sort of once every 2 weeks from February to June, and each time we read a paper and then we discuss it, and then someone gives presentations on it, and people write responses to it, and just engage with the material. And then at the end of that, the students get together with the mentors and do a intense research week where they work all the time.
Is this the first year that they?
I believe this is the 4th year, and maybe the 3rd or 4th year. Yeah.
Okay. Okay, so it's actually been going for a little bit of time now.
Yeah, it's becoming an institution, and
Okay.
and one cool thing about that is that you know, it's hard to finish a entire project in a week, but we've seen that that the work that gets started in these research weeks often gets finished later and will appear in future ACTs as talks and as papers. So, you know, that's so been cool. That's been fun. So
that's really cool. Yeah, I mean, has some stuff come from like last year's one, or like
yeah, I would have to bring up my list to know, but yeah, I know. Well, I went 2 years ago, and so did Sophie, the other organizer this year, and I know that it spurred a project that I'm working on. So, and it spurred a project that Sophie's working on, and our whole group has kind of developed in a lot of ways from stuff we learned at that time. So, and I know that there are,
no, I guess it's also really cool working with kind of younger researchers, because like they often like have really good ideas, you know, just like, you know, they bring things to the table that maybe you didn't necessarily think about, or like just having that input. I love that idea. I think having that like I think it gives people such a good opportunity to see what it's really like to work in applied category theory, and I think after that you'd probably be hooked. I don't think you would want to leave that community after that. I think
we certainly hope so. So
yeah,
we certainly hope so.
Awesome.
Yeah, I know we have sorry.
Yeah, kind of. Elena is talk about what happened in last year's ACT in one of the posters on Wednesday. So tomorrow.
Nice. Thank you.
And I think you're right. I think it's 2018.
Right.
But yeah, it's difficult to keep things going after. I think this version might be better. I think it's kind of still. I mean, if you have 4 years, 2 of them during pandemic times, life is difficult, right? It's not. I mean, one has to adapt, and I think adaptation is going on. It seems to me.
Yes, I believe that we have 2 papers from last year's. So one is Valeria's group, and one was Johnson's group. So where's Johnson? Johnson's first name. I'll look up the thing. Michael Johnson. Great. On lenses. I don't know if that was presented here, but it's on the archive. So.
Well, I think actually there's some stuff tomorrow on it. Also, there was some stuff on yesterday. Yeah, I think actually there's a really interesting talk tomorrow morning. First talk. So I guess having the Adjoint school like today, like the presentations today, would be pretty good preparation for tomorrow.
Yeah, and from 2019 we had 6 papers as a result. So
okay, cool.
For 4 groups, it's pretty good.
Yeah.
Yeah, impressive. More than 1 per group. Yeah.
Yeah. And that's not counting my group in particular, because we all went and did different stuff. But we learned all of that. We learned all the techniques we needed during the research week. So I would count them. So I see some of the current students are arriving now. I asked them to show up if they could at this time so that we could test out the technology, but I don't have any privileges to do that. But I don't know, just, yeah, so.
Unmute and test.
Unmute test.
I'm wondering, could you say something about how much maybe background, like how, you know, I'm not in math, I'm an engineer, so, but I'm, you know, working towards it. How much, at what level could I, you know, apply to the adjuncts?
Yeah, so that's a great question. I think we aim to have a mix of different levels of incoming knowledge to category theory so that people can fill in each other's gaps. So, you know, if you're already here at this conference and you've been understanding some of the talks, you're, I think, more than ready, I would say. The point of having the long lead up to the research week is for you to learn. You know, it helps to know, like, I would say, like the bread and butter of category theory, like what's a category, what's a functor, what's a natural transformation, things like this, maybe. If you have a programming experience in functional languages, you can adapt that knowledge. If you have experience with, you know, certain kinds of systems, you can adapt that knowledge, like systems theoretic things. And yeah, it's really going to depend on how much you wanna learn during the time. So I think you know, most of the time the directions of research are stuff that's off the beaten trail for regular category theory. So no one, you know, coming in really knows about them and learns about them. So you know, I encourage you to apply.
Yeah, I think I will for next year.
Wonderful. Wait, who's the host?
Cambridge, I think.
Oh, it's got the host has opened breakout rooms. To the school participants joining, I don't have host privileges, so I can't do the test. So we'll just cross our fingers.
David, in that case, should we stay on in case you get host privileges, or are we good to drop off and rejoin in 12 minutes?
Yeah, I think that's probably fine. I expect that the tea time's going on and the organizers are out there.
Got it. Cool. All right. See you shortly.
Hey.
Hello. Is it just us? What's
Yeah.
how? Okay. Is everybody?
It's everyone.
Oh, wow. Hello, everyone.
Hi. Hi. Is there a process for making all of the people who need to be co-hosts or sharing screen stuff? Has this happened?
Hi, Sophie. As far as I can tell, the organizers aren't here.
Oh no.
So, yeah, I've been here for about 20 minutes. So I think they left during the tea time.
All right.
Hi, Pablo.
Oh yeah. Hey, hello.
Long time no see.
It's true.
How are you?
Nice. Good, you?
Good. Good.
Man, where are you now, man?
I'm
Baltimore, man, Westbound, Boston.
Topos.
Oh yeah?
In
Nice.
Berkeley. Yeah. Which is very nice. Are you still down in Florida?
No, I'm in England now.
Oh wow. Nice.
Yeah.
But not in person.
No, I couldn't because I'll be moving very soon and I can't afford to like catch this Delta. I'm not fully vaccinated yet.
Mm-hmm.
Yeah, Oxford. But
where are you moving?
I'm just moving to London. I'll be commuting.
Oh, nice.
It's cool. But so are you there at the Topos fixed or are you just visiting? What's your
I'm just here for the summer.
Oh, I see. Nice.
It's really nice. Yeah.
What is it like?
It's really great. They got like you know, a few little office rooms and people move around and you know talk to each other about category theory and the weather's really nice out here. Something I'm experiencing.
Oh yeah, can't imagine. Wow, nice.
And I'm in an Airbnb with Christian Williams, Joshua Myers, and Owen Lynch.
Oh wow,
Right,
it's a
Owen.
fully
and we're on the hill. We have a large balcony that overlooks the bay, and it's just splendid. So
wow, just wow.
It's the digs.
Sounds amazing.
Say hi to Christian for me, David, if you please.
Huh?
Say hi to Christian, to William.
Oh, I will. Stelios says hi, Christian.
Oh, hey.
Says hi.
Oh, he's around. Okay. Nice.
I think he'll be joining for the actual event. I guess it's coming up.
Great, great.
Hey, Sophie. Hey, everyone.
Hey.
How's everything going?
Pretty good. I think we're missing some organizers to give us sharing privileges, but
I believe the organizers are at tea.
If you're in Google Slides, is there a way to share within window?
say it again.
If you're in Google Slides, is there a way to, when you, wait, present, okay, I figured it out.
Sophie, you are a co-host already, so maybe you can share with David, no?
I can't seem to make other people co-hosts.
Right.
No, they changed the co-host privileges with, in Zoom. So the default is now a different one from what it used to be. And so actually, Jamie just found out this morning that when I became co-host, I could still not help my speakers to.
Oh no.
Hi, Jamie.
So as co-host, the only thing you can do is mute and unmute everybody.
Oh, wow.
It's so much power.
So you do need someone, you do need Jamie then to come in and help.
Yeah. Yeah, and I think I see somebody there.
Oh,
great.
Hi.
Good. Cambridge, can you guys give some people here the co-host and sharing abilities? Daar is Colin. Okay.
Hey, Colin.
All the speakers should also have sharing privileges, right?
Yeah.
Mhm.
Sure things go a bit smoothly.
I think maybe the speakers who will be sharing their screen should mention in the chat.
Oh no, it says use the raise hand.
Raise hand. That's
feature.
Okay, great.
Stelios, you have to do it in your Zoom under reactions. Press raise hand. Got it.
Stelios, it's below that. There's another raise hand, and that puts you automatically in the front of the queue. It makes it easier for people to find you.
So not on reactions, participants.
It's
Raise hand. Raise hand.
You found it.
Got it. Yes. Thank you.
Great. Have we got the speakers all co-hosts now? Okay, let's get started then. So welcome everyone to the Adjoint School session at ACT 2021. Just to begin, I'll say a few words about the Adjoint School. So the Adjoint School is now in its 4th year. It's a student-run, student-organized school aiming to foster an open-hearted and open-minded environment where new applied category theorists can develop the skills of research. So it's based around small group mentoring, and we're very lucky to have a group of 6 leaders, leading faculty members in the applied category theory community, taking approximately, this year, 18 students through the processes of beginning from reading the literature, reading papers, collaborating, writing blog posts and giving talks and writing papers. The school begins with a competitive application process in December, January, and then has this 6-month online reading course in the first part of the year before an intensive research week that happened last year, sort of full-time. It's often in person, unfortunately not this year, but where everyone gathers this year virtually to to work intensively on a problem that's set up by the mentors with the reading groups in mind. So the readings lead up to these research problems. This year, at least one group, the photo here is from here in Berkeley, where one group managed to meet partly in person and had a lovely time having lunch, on a picnic. So this year, well, this session is after this 6-month process. Students often come from a wide variety of backgrounds. The core, it is usually graduate students in mathematics, computer science, but the students range from undergraduates to professional programmers and across fields from mathematics, computer science, programming, but also chemistry, physics, and various applied sciences, often depending on the subjects of the school. And so now the students will present some of the work they've been doing over the past 6 months, but in particular, the work of the past week. So it's research in progress, and it's just a report. So we know, as a community, know what's going on in the school, but also an opportunity to welcome the students into the community. And hopefully we'll see them around throughout this conference, not only at the talks, but at the social breaks and so on. This year, the school was organized, it's student run, it was organized by Sophie Libkind and David Jazz Myers, and we're lucky to have these 4 groups. Yes, thanks to both of them. They've done, it's an amazing effort to organize this whole process. It takes a whole year, and they've done an amazing job. So without, the groups will be presenting each group around 20 minutes, I think roughly in this order. And so without further introduction, let's get into it. The first talk will be by Stelios Tsampas from this coalgebraic dynamic logic group, mentored by Hella Hansen and Clemens Kupke. And the talk is titled Safety for Bisimulation for Coalgebraic Dynamic Logic. So, right. Shall I stop sharing and Stelios, can you share?
Sure thing.
Perfect.
So, all right. So I'm Stelios, like Brendan said. This is the coalgebraic dynamic logic group of the Adjoint School 2021. I'm going to talk to you about one of the 2 topics that we covered in this group. So we're split into 2, and 2 of us, myself and Anthony, did safety for bisimulation, and the second topic will be picked up by the other 2 students. I want also to thank everyone who organized this. This was a great experience, learned a lot, and let's get right to it. So I'm going to begin with a crash course on coalgebras. So coalgebras are this remarkably simple mathematical structure, which consists, first of all, of an endofunctor. Let's just stay in sets, in the category of sets, F. And an F coalgebra is simply a certain object in this category, a certain set S, and an arrow from S to Fs. We call S the state space of the coalgebra, and AS, the transition structure of the coalgebra. And these are used to abstractly describe systems of sorts that perform sort of transitions over time. A very prominent example of such coalgebras are label transition systems. And the concrete definition of an LTS is that of a triple S, this arrow, this transition structure, and a set of labels A. So an LTS is a relation from a set of space down to transition states here, down to like a pair of labels and other states. And this describes essentially how a certain element of the state space evolves over time, but also outputs a certain label. So if we define an endofunctor B in the category of sets as B of X is mapped to the power set of A times X, then you can see that coalgebras of this endofunctor are in a correspondence between label transition systems. So for instance, if you use this notation here, which is widely used in LTSs, that says that S transitions to, this would have been S prime rather, so S prime, suspend our disbelief, and outputs A, is essentially saying that the pair A and S prime belongs in whatever the mapping of S is under A of S. And that's basically, coalgebras. And this is a remarkably powerful framework and a very general one. So when defining coalgebras, I believe that the most fundamental notion that comes with it is that of a coalgebra homomorphism. So now take two coalgebras, AS and AT. A homomorphism between those two, F, is a function, or in general an arrow, right? That makes this diagram commute, which is like the obvious diagram of that expresses compatibility of AS and AT under F. And we can generalize this a little bit. And instead of having like a simple function from S to T, we can have a span, right? We can have a relation. So take a relation R here, that is a subset of the Cartesian product between S and T. So a relation R is an F bisimulation if there exists an F coalgebra on R here, AR, so that the two legs of the span of the relation are both F coalgebra homomorphisms, like this. So you can see an example here of why this is a useful notion and why this actually captures behavioral indistinguishability. So let's take an example. Bisimulation R in the category for LTSs goes like this. So for any S prime such that the S goes to S prime and emits a label alpha, if T is related by bisimulation to S, then there exists a state T prime such that T transitions to T prime and emits the same label alpha. Also, we want those two transition states to be also related under R. And we have to take this both ways. This is like a symmetric thing. And I would say, to me, the way that I understand it abstractly is that bisimulations are the relational analogs of coalgebra homomorphism. And to me, this is important because I'm more abstract-minded. And I can just simply, eschew the, bisimulation and just speak about coalgebra homomorphisms to simplify things. So now, this was the crash course on coalgebras. I'm going to be talking a little bit about something concrete, about PDL. A PDL is a special form of modal logic, is a two-sorted modal logic that is used for the correctness of programs. What I like about PDL, or what I find special about PDL, is that it has two sorts. One of the sorts is for formulas here, and phi here is a formula, and P is like an atomic Boolean proposition, and you have other operations in there, which are simple first-order logic operations. However, if you step in here, you have a little gamma there. And for people who know modal logic, if you forget about the gamma, this is basically the square operator, right? It's like the force operator. Sadly, I don't have the time to say more on it. But what you can keep in mind is that we can speak specifically, you can make propositions, not only for a particular system, where phi is a proposition and we have some system, but we can parameterize the system over here, the system gamma. And that's where the second sort comes in. The second sort defines programs inductively. So we can build programs in an inductive manner by having a certain set of pre-existing programs and certain operations like the union operator, which describes the mixing of two programs together, the composition operator, which says that, okay, one program after the other, and then this weird clean star operator, iteration. So I would say that's a bit more than a modal logic, in that the set gamma to me resembles a set of terms programming languages, which makes sense because you want to reason apparently just about one program, but many. two basic facts about this kind of logics. Formulas are invariant under bisimulation. I'm not going to explain more because we care about the second thing, about safety. So what we care about, that program operations are safe for bisimulation. So if R, take any R, the bisimulation between programs H1 and H2, so you have two programs, then we want R to be a bisimulation, or rather it is true, for the union of these two programs. And again, I have to apologize because I don't have the time to explain more, sorry. But I think things will get more clear as soon as I get to the abstract. So the idea of this group was to take PDL and go to coalgebras, abstract and contour using coalgebras to what's called coalgebraic dynamic logic. So what are formulas abstractly? Well, actually, we don't care. What we care about is what are programs abstractly, what are programs operations abstractly, and what is bisimulation safety abstractly, and how do we relate those with coalgebras? So programs in general are coalgebras. That's like the abstraction. Programs operations are operations on coalgebras. Makes sense, right? And bisimulation safety in this setting is a sort of functoriality or preservation of bisimulation. It is functoriality. We have to like explain it a bit more, but for now, I think preservation of bisimulation is more clear. By the way, coalgebras for what? We're going to assume that we have coalgebras for a monad. So our endofunctor has a monad structure, taf, eta, and me. We will also assume that home sets in KLT have an order structure, and there's a binary join operation. You know, so you can take like two programs and stick them together. So let's talk about the safety for the semicolon operator, so for the sequential composition. So like I said, the meaning of H1 after H2 is the system that does H2 after H1. Abstractly, we can say that the meaning, if this defines the meaning of H1 after H2, is basically the Claesley composition of these two coalgebras programs. And we want to show that this is safe, right? So how can we do this? Well, it's pretty simple. Say now that H1 and H2, or rather you have F, which is a bisimulation between H1 and G1 and H1 and H2 and G2. So now if we do a Claesley composition, H2 after H1 and G2 after G1, all of those squares here commute. Whoops, sorry. They commute.
Oh, is 2 minutes okay?
Yeah, it's absolutely okay.
Okay.
So this commutes because F is a bisimulation. This commutes because functor T preserves the square, right? The commutative square, and me is natural, so this is it. So this is basically proving that the sequential composition is safe for bisimulation. We can do the same thing for operation U, no? It is the meaning, which means that it is a system that combines U, H1 and H2. Sorry for the typo. So abstractly, we can simply use the join operation of the enriched category. And we can use a similar technique to show that this operation here is safe. And this is rather easy in both ways. We're just using naturality, right? In that the binary join of the home sets is defined by a certain natural transformation. The harder case was that proving that the clean star operation is safe. So we wanted to say, for instance, that if we have a bisimulation on H, between rather two systems, H and G, that there is a bisimulation in the systems H star and G star. So this was harder because you have to define H, or rather the clean star operation is defined as a fixed point. So you need to deploy some basically initiality, induction, the least fixed point rule. We do have a proof on that, which is ready. It is. And now I'm going to leave it to my colleagues for the second part of the presentation.
Great. So now to continue this presentation, we have Amin Karamlou and Gabriel Goren. So, thank you, Stelios.
So can you hear me now? Great. if everything's working okay, then now Amin and I will talk about another problem that we've been working on in the context of trying to understand this stochastic game logic from a coalgebraic perspective. So first of all, what is this stochastic game logic? So Stelios already mentioned PDL. So game logics turn out to be something a bit more general than PDL, and PDL can be considered a fragment of game logics. So the idea here is that instead of programs, we have games. So game logics describe two-player games through the capabilities of players for forcing certain outcomes when playing those games. And the way that game logic does this is by extending propositional logic with these modalities, like the ones in PDL, but now corresponding or being indexed by games. So here we have that the intending meaning now is that for this expression here with a diamond indexed by gamma is that player one has a strategy to force phi to hold when playing game gamma, right? And the same as before, as in PDL, games can be combined together, and we're also interested in particular in sequential composition of games. The stochastic game logic extends this situation by allowing expressions with a probabilistic component. So we have these modalities like the one here, whose intended meaning is that player one has a strategy to force phi to hold when playing this game gamma with probability greater than Q. So this is an actually interesting situation to consider. And now, well, how does this fit into the coalgebraic dynamic logic framework? Well, the semantics of game logic is a standard game logic is usually given in terms of neighborhood models, which similarly to the LTS case as Stelios mentioned, turn out to be coalgebras for a certain functor, which is the monotone neighborhood functor, which I will not explain right now. And then when we add this stochastic layer to our models, we would expect that the models for this stochastic game logic, in particular, a discrete version of it, should be coalgebras for this composite functor MD, where D is a functor that sends, what is the distributions functor that sends X to finitely supported probability distributions on X. Now, the thing is that, as Stelios already mentioned, in coalgebraic dynamic logic, we need a monad structure on this functor, for instance, to define the composition of games by Kleisli composition. However, MD is not known to be a monad, even though there are standard monad structures on both M and D, right? So we'd like to know whether MD is a monad, whether there is some structure that we can use, or rather we need to extend the framework to account for this obstruction. So one way to look at this is by looking at distributive laws. So a sufficient condition for MD to admit a monad structure is the existence of such a distributive law, which is a natural transformation of type DM to MD, which must satisfy some axioms that are shown here. So as a first step, we looked at the possibility, what if there isn't such a distributive law? So there are these existing no-go theorems that could disprove in principle the existence of such a distributive law of this type, and therefore there's no, it doesn't make sense to look for it, right? So, so we looked at these no-go theorems, and something important about these theorems is that they are presented in terms of the algebraic theories corresponding to the monads. So before, I didn't really say anything about the functors that we've been looking at, or the monad structures on them, but it's important to keep in mind that giving an algebraic theory for a monad is actually describing the monad. It's giving essentially the same information. So for instance, the algebraic theory of this M functor has terms built out of variables using the two operators join and meet. So for instance, we have terms that look like this, and then valid equations include these ones. So we have both terms and some equations that must hold between them, and that's an algebraic theory. And this turns out to be the theory of distributive lattices. On the other side, we have the algebraic theory of D, which is a theory of convex combinations, where we form terms by taking some variables and then using these binary operators plus sub p, where p belongs to the unit interval. So using that these are the theories for these two particular functors, we checked this list of different theorems, and at least one hypothesis on these theories fails for each of the no-go theorems. So here you have a table that we took out of the paper that we've been looking at, and I've crossed out some of the axioms that that fail for a particular choice of functors. So this is showing us that these no-go theorems don't say anything directly about our particular case. Right, so there ends my part of the talk, and now Amin, I'll just keep showing the slides.
He's going to keep showing the slides. Okay, so next slide, please. Cool. So I guess in the spirit of a hybrid conference, we thought we'd do a hybrid presentation as well. So Gabo talked a bit about the no-go theorems and what would happen if we could prove that there isn't a monad. But at some point during the research week, we started to think maybe we're being a bit pessimistic. So I'm going to talk a bit about our approaches towards proving that, in fact, there does exist a distributive law between the two monads that we're considering. Next slide, please. So the first thing to talk about are these composite theories. What I mean by composite theory is a special kind of algebraic theory. So just like you can talk about monads in terms of their corresponding algebraic theories, you can also talk about distributive laws between monads in terms of algebraic theories. Specifically, we know that there is a distributive law between M and D if and only if there's this composite theory of the corresponding algebras. Now, what does it mean to have a composite theory? Well, you really need to satisfy three things. First, your theory needs to contain the axioms of both the theories of the two monads that you're considering. Secondly, any term in your theory needs to be equal to what's known as a separated term. So I'll talk a bit more about what that is. And finally, there's this condition of equality modulo. I'm not really going to get into that one, partially because I myself don't have a great intuitive understanding of it yet, to be honest with you. Next slide, please. So we have the theory of distributive lattices for our monad M, like Gabo mentioned. And we have the theory of convex sums for the distribution monad. And now we're going to construct a candidate composite theory. And this is sort of done by analogy with the fact that doing a similar thing in the case of the power set monad and the distribution monad gives us what's known as a weak distributive law. So we use this idea to sort of come up with our candidate composite theory here. And you can see on the slide that I've added these two new axioms to the theory. These are sort of saying how you would distribute the convex plus operator over your joins and meets of your distributive lattice. So we're adding this axiom to the axioms of M and D. Next slide, please. Okay, so what we want to do now is check if this is in fact a composite theory, right? Because if it is, that proves that we have a distributive law. So the first thing to check is that it contains all the axioms of M and D, and hopefully from what I showed you on the previous slide, everyone can agree that it does. The second thing to check is that every term can be rewritten as a separated term. Next slide. So, okay, I'll give you some intuition for what separation is. I won't give you the full definition, but the idea is that to have a separated term, you can write any term in your algebraic theory out as something that has the structure of M on the outside and the structure of D on the inside. Maybe this will be more clear if I go through an example. So on the slide, I have a term U, and I have some terms that are equal to U. You can see if you look at it that I've just applied these axioms on the previous slide, mainly the new distribution axiom that we introduced. And on the final line, I get to some term where if I replace the inner part of that term, so anywhere where we have these convex plus operations, I sort of replace those with variables. That gives me a term that really would be a valid term in the theory M. And that's how you can get separation. Now, of course, this isn't a proof because we would need to prove that this is given any term in this algebraic theory, you can always separate it. But this gives you some idea of how it is, how you would go about this. Next slide.
I mean, 60 seconds, if that's okay.
Yeah, I'm almost done. Okay, so yeah, and in fact, we think we have a proper proof that every term can be separated. You just need to do some simple induction. There's nothing too fancy going on there. Next slide. So I guess the final thing to check here is the bit that I've swept under the rug, which is this equality modulo definition, and I won't really get into that. I will say that we have been discussing recently whether this is the best way of checking our distributive law, because we could also just check the 4 axioms that Gabo showed at the beginning of the presentation. That would be another way of going about checking whether a candidate is in fact a distributive law. So that's also something we will look into. Okay.
Okay, great. Let's thank Amin and Gabriel and the whole group. Great. Thank you. So now from Simon Willerton's group, TA'd by Titan A. Bradley and Callum Reeder, we have Owen Lewis, Elise Catania, Hussain Kadhem, and Matthew DiMeglio speaking about optimization and perfunctor nuclei.
All right. Oops. Sorry, I guess that the screen sharing and present mode aren't entirely compatible. Is the font big enough in this format?
No, we're seeing 2.5 slides at once. Is it possible to get?
All right, let me start over here.
Maybe you could just zoom in without using present mode.
Okay, yeah, let me try that. Okay.
Yeah, that's much more readable.
Does this look better?
Yep.
Okay, great. Okay, perfect. Yeah, so our topic is applications of profunctor nuclei. We'll mostly talk about our research week activity, which focused on optimization, but maybe I'll just start with a little introduction to nuclei in general. So we'll always work in an enriched setting. So that means that a profunctor maps a pair of V categories C and D down to the enriching category V. So given a profunctor P, we can form the so-called generalized Isbell duality, which gives us an adjoint pair P upper star, P lower star, which relates the category of presheaves on V and the category of op-co-presheaves on D. And then the nucleus of P is the center of this adjunction. So that's the fixed point of the sort of 2 round trip compositions that we get. So I think a good way to make that a little bit less abstract and build some intuition is to develop an analogy with linear algebra. So the starting point is the observation that an m by n real matrix is nothing other than a selection of a real number for each row index, column index pair. So if we abuse notation a little bit, we can write our matrix in this kind of profunctory way as a map from the product of the row indices and the column indices to the reals. Next step is that adjoints are a little bit like transposes. So here we had P upper star and P lower star relating V to the C and V to the D. Here we have M and M transpose relating Rn and Rm. And then the punchline is that the nucleus of the profunctor is a little bit like the singular value decomposition of the matrix. So the right and left singular vectors of M are just the eigenvectors of M transpose and M transpose M, which sort of looks a lot like the definition of the nucleus as the fixed point of P upper star, P lower star, and P lower star, P upper star. So just like SVDs show up in a lot of applications of linear algebra, profunctor nuclei show up in a lot of applications of category theory. So during the school, we looked at formal and quantitative concept analysis, the Legendre transform, the Dedekind-McNeil completion, the tight span of a directed metric space, and then during the research week, optimization, which we'll go into a little bit of detail on now. So Elise will talk shortly about a formulation of the optimal transport problem developed originally by our mentors Callum and Simon. And now Matt and I will talk some about multi-commodity flow, building on earlier work by Hirai and Koichi. So following that earlier work, we'll work in a slightly simplified statement of the multi-commodity flow problem. So we're given a graph where each edge is labeled with a positive real capacity. So you can think about maybe a sewer network where each pipe has a diameter or something like that. And then we're given a set of source nodes and a set of sink nodes, and someone has offered to pay us for sort of flowing goods between sources and sinks. So for each source sink pair, we get some number of dollars for each unit of flow between them. And then our goal is to sort of choose the best way to route flow along the source sink paths in the graph without violating any of these capacity constraints on the edges. So to introduce the category theory, we actually want to work in the linear programming dual version of this problem. I'm going to skate over a lot of details here, but the main point is that solving the dual problem amounts to choosing some kind of price delta for each edge in the graph, such that the capacity weighted total price is minimized, subject to some kind of compatibility constraint with the primal version of the problem. So Hirai and Koichi, the earlier work I mentioned, worked in a slight, they made some slightly stronger assumptions. So in their version of the problem, there aren't separate source sets and sink sets. Instead, there's just sort of a single terminal set S. And they also assume that the bounty function P is a directed metric on S. So under these conditions, they showed that there is an optimal choice of these costs delta that embeds isometrically into the tight span of this directed metric P. So I alluded briefly to the fact that the tight span of a directed metric space is one way that profunctor nuclei sort of manifest themselves. So now I'll hand it off to my teammate Matt in recorded form, who will sort of develop the story a little bit and sketch how we can have a kind of categorical generalization of the Hirai and Koichi result.
Okay, great. Owen, I am not Matt, but I am going to play the recording of Matt to follow up for Owen. So let me just pull up Matt's video for everyone. One second. Okay, actually, I seem to be having trouble with my settings for screen sharing. Okay, let me try it this way. Oh no. Okay, can you see this video screen now?
We can, but it's I'm seeing sort of a diagonal pattern across the screen.
Oh no. Okay, wait, I'm just gonna click play and see, does something happen?
Hi everyone, my name is Matt Meglio and I'm a researcher.
Is that
Got the sound but no video here.
sound but no video? Okay, Owen, do you wanna try playing Matt's video since you shared your screen, okay?
Yeah, let me give it a shot. Give me 1 second.
Okay, sorry everyone.
Just in the interest of time, I want to make sure the next two speakers on your team have ample time too. Is it possible to cut to them and maybe we can distribute the video after?
I think maybe you were just sharing the wrong screen. So maybe you could just try sharing, because when you share screen, you pick a window and maybe you had the wrong window selected so we could hear it. There we go. That looks more like it.
This looks good?
We can see it, yeah. We can't hear it now, though.
I noticed. I
Play it locally. If you email the link to Yanis, and we can come back to this. We
Yeah.
can try and play it locally.
I'm sorry. I think I'm going to step in just in time, and we'll distribute this video afterwards. But I don't think we have time for another 7 minutes at the moment. So let's get to the next two speakers, and then we'll
Sure.
Thanks.
I'll put the link in the chat.
So is it Elise up next?
Yes. Owen, are you still sharing? Okay.
I think you should be good.
Okay. Okay, so I will spend a few minutes discussing optimal transport, and momentarily we will see how enriched categories and profunctors unfold very nicely from this problem. So first off, what is the goal of optimal transport? So the idea is that we want to transport goods from as suppliers to our receivers. So here I have 3 farms that are supplying, we can think of dozens of eggs to a few supermarkets. And so we have a cost to transport 1 dozen eggs, which we denote as K sub ij, which is just a non-negative real number. And we have an associated cost matrix with this. Okay, so each farm has a certain amount of supply, and each grocery store has a certain amount of demand. So we'll denote the supply as sigma sub I and demand as rho sub I. And so we have a choice to be made, because let's say Wegmans, a grocery store, wants to know, well, how many dozens of eggs should they buy from each respective farm? So a transport plan is a choice, alpha sub ij, for each ij, such that we have this summation of alpha ij's has to be greater than or equal to rho sub j for all j. So that's just saying that, well, my demand has to be met. And then also we have to have that the summation of alpha ij's has to be less than or equal to sigma sub I for all I. So I just can't exceed my supply. And the cost of a transport plan is the summation over all ij of k sub ij times alpha ij. And then an optimal transport plan is a transport plan that minimizes this total cost. Okay, but what we really care about here is the dual optimal transport plan or transport problem. So now what's going to happen is a transport company comes into play, and this transport company has an alternative pricing structure. So instead of caring about the actual route taken to send my eggs over from the farm to a grocery store, the transport company will have it such that for each supplier, the company pays a fixed price per unit, and for each receiver, it charges a fixed price per unit. Where U sub I minus V sub j is less than or equal to K sub ij, and that's just due to the fact, well, if their cost was not less than my cost, then why would I be hiring them? So given this dual plan, the transport company's total revenue is this expression here. And so our goal for the dual optimal transport problem is to maximize our total revenue. So exploring this a little further, given that the transport company fixes a price V at the suppliers, they want to think about, well, what's the best that they can charge? We'll denote that V hat at the receivers, but still remain competitive. And so we can fix J, and then we get this inequality, and doing some algebra, just moving V sub I over, we can take V hat J to be the minimum of Kij plus Vi over all of I. And similarly, the transport company can think about what are the lowest prices. We'll denote U tilde at the suppliers that are competitive but yield the biggest revenue. And so we have this similar inequality going on, and we can take U tilde I to be the max of the maximum of Uj minus K sub Ij over all J. And the function of this max and 0 is just to ensure that our U tilde I is non-negative. And then we say that a price plan UV is tight if V hat is equal to U and U tilde is equal to V. And so the exciting part in all of this is that we can model the situation with enriched categories. So we can regard S as a discrete R bar plus category where the distance between two suppliers is 0 if they're the same and infinite if they're not. And so really what all this is saying is that we don't really care about distances in this setup. And so if we regard S as a discrete R bar plus category, then an assignment V of prices to each supplier is just a co-creation on S. So we see that we have this duality between that hat operator we saw earlier and this tilde operator. And then regarding the cost matrix K as a profunctor, we can see that the cost matrix K is just an R bar plus profunctor from S to R. And there's a well-known adjunction. So left composing with K is going to be left adjoint to taking right con lifts along K. And in this particular case, if we use the formula for composing with K and we work out what this actually means for this category, well, we see that's exactly just V hat J that we defined earlier. And doing the same thing, taking the definition of the right con lift of V along K and seeing what this means in this category, we see that's, well, that's just U tilde of I. And so we can see that in the center of this adjunction, we get precisely tight price plans. And with that, I will hand it over to Hussain for the last couple of minutes.
How are we for time? I think it's fine to skip mine if we're
pretty tight on time, but if you've got sort of 2 or 3 minutes, I mean, thanks for that gesture, but would love to hear from you for a few minutes if you've.
All right. Do you see my screen?
Yes.
Okay. So very quickly, Matt and I ended up investigating how to categorize this more general framework of optimization problems and duality. So in general, say we have a function f of x from some space x, which is nice, to R bar, which we want to minimize. So so in general, this doesn't have to be a linear programming problem. It's just any function which we want to minimize. One strategy which is standard in the optimization world is to introduce what is called a perturbation function. phi of xy such that so we introduce a perturbation function phi of xy such that phi of x 0 is equal to f of x, where the y's here are in some other space depending on our optimization problem, which we use to parameterize kind of how big this perturbation is. So for example, if we want to make the linear programming problem fit into this framework, we would choose y to be x dual, something like that. And so there is a theorem which is, we introduce another function. So h of y, which is just equal to the inf over x of so basically h of y is you fix y and then you take the minimum over all of x of phi of xy. In particular, the optimization solution is given by h of 0. And so there's this theorem that if our functions are nice enough, so if they're lower semi-continuous convex, we have that the dual solution is given by so given nice enough functions, we can recover the dual solution as the double convex conjugates of h, and it is equal to a maximization problem on negative the convex conjugate of phi. Here the convex conjugate is the Legendre-Fanchel transform. And so if you say these things, time?
Yeah, around time.
Okay. Yeah, so
you have a sentence to summarize?
Yeah, so if you say these things in the right conjectural categorical framework, you get kind of this theorem out of the general Kahn and Isbell adjunction of profunctors.
Oh. Okay, well, let's thank the entire group for their presentation. It's very interesting. And now, apologies for moving quickly on, but we have now James Fairbanks and Evan Patterson's group on the categorical and computational aspects of C-sets. And first up speaking as Angeline Aguinaldo and Kris Brown on implementing polynomial functors in CATLab.
Great, thanks, Brendan. Can everyone see my screen and hear me?
Yep, we're good.
Okay, great. Okay, well, we're over the next 10 minutes, Kris and I will be talking about our progress with regards to implementing polynomial functors in CATLab. So what is a polynomial functor? Well, we're all familiar with the polynomial, what a polynomial is. So David Sivak and Nelson Yu are proposing another terminology for viewing these polynomials. And just so you can see it here, there's this forest representation of a polynomial that we can use to intuit the dynamics of mode-dependent dynamical systems. And so the way that you read this is by looking at each of the dots, and each of the dots correspond to a term in your polynomial. And every direction corresponds to a unique value that that particular term can take. So we call these arrows directions, and every root in this forest a position. So when we think of polynomial functors, we can think of them as a sum of representable functors, where the functor is a functor from set to set, and A being a set. So the mechanics of a polynomial is actually very useful in describing mode-dependent dynamical systems. So for example, suppose we have an interface of a system where we have 3 different modes. Though we're in the same system, it may be that the particular state that you're in may afford us different options or different behaviors in that particular mode. And so just in an example here, suppose we have 3 modes in a system, and in mode 1, we have the option, a few options. We have 4 options to select, option A, B, C, or D. The semantics of it doesn't matter at the moment, but just imagine that there are 4 options to select. And in the second mode, we have 2 options, E and C. And in the third mode, we have 3 options, F, G, and C. We can view this, these different modes as the forest representation, as I showed in the previous slide. And it can, when you add these all together, it can represent the entire dynamics of a mode-dependent dynamical system. And so, as I said, the mechanics of a polynomial is actually pretty handy for this. So, for example, you can notice that C is available in all modes, all 3 modes. And so with the polynomial, we can factor this out and just pull out the C direction from all of these different polynomial terms and add them all together and represent them as kind of a multiplication or a product of 2 modes. And so the benefit of this is if we have multiple, say we have 2 systems and we want to compose their modes together and their options together, we can do so in a polynomial way, and it'll result in the proper construction of the combination of all those modes and options. Okay, so I'm just going to walk through a quick example here. So we worked through, to kind of test this out, we worked through an intuitive example called the happy refrigerator. And we have, imagine a refrigerator in which its capacity is a certain number of drinks. And there's 3 modes available in this refrigerator finite state machine, where in one state in which there's no drinks, we can only add drinks to the refrigerator. And in the case where we're at capacity, we can only take drinks from that refrigerator. And in all the intermediate states, we can add or take drinks as we wish. And so the other benefit of the polynomial functor is that we can apply labels to each of the terms. And so suppose we're in this state of our happy refrigerator where we don't have any drinks and we can't add or can't take anything. We can label that particular mode as being sad. So you can see the sad phase here. And then all other modes in which we can take drinks, we can consider them as that we're happy because we can have a drink from the refrigerator. And so we can represent this finite state machine as this polynomial functor, as you can see here. So with this example, we kind of move forward to try to see how we would implement and encode the finite polynomial and the coalgebra for it in CATLAB. So this is just a demonstration here to say that we wrote some code throughout the week so as a user can specify a dynamical or the coalgebra of this dynamical system. And you can describe the behaviors at every state of the dynamical system, encode it, and then ultimately run the example. So moving on to the next slide here, you can see in the case of our happy refrigerator example, we've encoded our polynomial dynamical system with the polynomial functor that we described, the number of states being 5, in that there's 4, the capacity of the refrigerator is 4 drinks, and then there's a state in which there's no drinks. And then we described at every state the mode that particular state is in and the available behaviors, and also provide an initial state. And so what you just saw was a little demo of the dynamical system running and a user providing input at every state of the system so that it can kind of move to the next state. And that was all implemented using the finite polynomial library or module in CATLAB. So at this point, I'm going to hand it off to Kris to talk about our next steps regarding a new example of universal programmable machine and some additions or some user interface tools.
Can you stop sharing?
Mm-hmm.
Okay, thanks.
Just a heads up on time, 4 minutes, is that okay?
That's perfect. Okay, so I want to talk about actually the underlying representation in CATLAB for what Angeline just talked about. In CATLAB, we work heavily with C-sets, which are functors from some indexing category into finite sets. And with the schema on the left, we can represent a set of directions that are indexed by their position. But if we want to represent a polynomial, we need to explicitly represent in memory each direction and each position, which means we cannot represent polynomials that, for example, take an arbitrary integer valued inputs or outputs. And that means that we can't modify our happy refrigerator to have an arbitrary number of drinks. So to have a more motivated example for why we want to represent infinite polynomials, I want to introduce the idea of an AB Moore machine, which is specified by two functions, update and readout. Now, an arbitrary Moore machine could be represented with a simple wiring diagram and giving some dynamics. But we want to explicitly consider the programming of this machine as its own behavior. So we could imagine these extra modes by which we interact with it. So we could tell it how to update its readout function by giving it pairs of states and outputs to give when you're at that state. So now the functions themselves are actually in some sense part of the state of this machine. And in order for this to be useful, we would need a way of toggling between these different modes. And this yields our polynomial interface, which looks like this, where this first term is basically the switch to switch between modes, and these correspond to the various modes. And we can see what that switch is doing by factoring in a different way to show that we're really just adding this extra option, this extra input to each mode. So now we want to work with infinite things so that we can convert strings to ints or various reals to other different data types. So we need actually more structure to our polynomials so that we can separate the finite combinatorial data from the sets that we're going to treat as arbitrary sets. And the naming here comes from the mode-dependent wiring diagram case, and I hope this will make more sense when I give an example. Here are some sorts of polynomials we can represent with this formalism on the left, and also some that we cannot. So now let's ask ourselves, how can we represent this data structure within CATLAB? So we're going to have a different C-set, but it's actually going to be an attributed C-set pronounced in Atchit. And this is going to augment our indexing schema with data types, which have different semantics from just these, the combinatorial data where identifiers have no meaning. So the non-combinatorial data the canonical example would be the weights of a weighted graph where the weight of 7 actually has some meaning. It's not just some arbitrary element of a set of reals. So they're actually implemented with arbitrary Julia types and should be preserved on the nose by morphisms. So let's get into what this actually means with an example. I'm going to do an instance of this Atchit by assigning finite sets to each of these objects. I'm color coding the signature to show you that what the signature really is there's one of these for every single distinct summand in the polynomial. And for each of those, you have to say which term, which mode it belongs to. And also every single letter here, which denotes an arbitrary set, maps into type. And for all of the outputs, you have to say, well, which mode did it come from? And for each input, you have to say which summand did it come from? And by extension, you can compose these two to find out which mode it came from. So this is how we represent the data underneath, and we can implement polynomial operations such as addition, multiplication, and tensor product on this data structure. So now that we have these operations implemented, we can do some important computations as shown here, but more importantly, we can build complex polynomials from these simple operations. And now we've just got started with this, and our next step will be to implement dynamics, as Angeline showed with the finite polynomial case. and basically do that same thing now with this richer data structure. And lastly, I just want to thank the Adjoint School in general and our mentors for guiding us through this project. So thank you.
Okay, we'll save applause for this group to the end. Next up is Amy Searle speaking about computing Ising models graphically, DPO for Markov chains.
Is it working? Okay, nice. And then the slides. Yeah. The scrolling doesn't seem to be working. Ah, cool. Yeah. Yeah. Okay. So can I start?
We still don't have slides in the remote version.
Is it working now? No.
Sorry, we're just going to leave and join again. It seems to be doing this repeatedly.
Well, waiting, does anyone have any questions for any of the groups? Maybe it's best to just type them in the chat.
ACT or yeah, I think it could be good.
Yeah, cool. Okay, I'll get started then. So my group is looking at C sets as well, but we're specifically looking at how double push-outs can be used for Markov chain simulation. So yeah, this was my group, as well as Owen and Kris, who helped write some of the code for us. So before I get into the sort of main project, I'd just like to say that as part of this project, Algebraic Julia, and specifically it depends, okay. Specifically it depends on this package CatLab, which is sort of gives this way to implement C sets in Julia. So Evan and James are working on this, and you can look at the GitHub or whatever. So these C sets are really just code-free sheaves. So they go from some index category C into set, right? Another thing which is going to be important is a slice category. So just quickly to recap what that is. So given some category C, the slice category is noted C over some specified object C, which I've labeled in blue. And what is the objects are choices of these objects X together with morphisms from that choice of object into C. And then morphisms are just the morphism G such that a triangle commutes. So we're going to use this to build a schema for the Markov chain. And in particular, we have this isomorphism of the slice category from, so we have the functor from C to set, so the C set, and we're going to take some elements of it, X, and we're going to look at the slice over that. And this is isomorphic to the functor from, so the category of elements of the functor X, which is this kind of like integral sign of X. And that's going to be useful for us when we speak about states of our chain. So for example, if you look at directed bipartite graphs, you have the slice of the C set is this thing on the left, X, and the category of elements is going to then give you this span, which I have on the right. And then what we want to do is we want to look at C sets over the span into sets, and that's going to, F is then going to be isomorphic to our actual state of the system. So we're looking at the Ising model, which obviously the machinery of category theory is a bit too heavy for this, but this is kind of a well-studied Monte Carlo Markov chain example. So we sort of just thought we'd look at that first. And so the slice is going to be this thing on the left, and then the category of elements, which is going to be our schema, is this thing on the right. And maybe I should say what the Ising model is. So it's this, it's top left on that side. And we have two types of nodes, so blue nodes and orange nodes. And these correspond to either spin up or spin down. And then you get a yellow edge between two different colors and a gray edge between the same color. And I haven't put down a Hamiltonian, but the idea is that if you have an edge between two different colors, it's going to sort of, I mean, if you want the whole thing to line up, the spins will line up like in a magnet, then that's going to contribute more to the energy. So the idea is that this thing is going to update its state until all the spins are pointing in one direction. And that's the kind of like Markov chain part, which I don't really go into detail about. Okay, so our states then are going to be isomorphic to these functors from the schema into set. Okay, that's what I've just said. Okay, and then the rewriting part, which is you can think of as the actual time simulation, is going to be this double push out. So we have these two push outs, the one on the left and the one on the right. And at the top, you have the span, which is going to be the rewrite rule. And what it does is it says, okay, we have this piece of our total Ising model L, which we want to replace with R. And so the difference between the two spans are exactly this L and R. So in the yellow span, in the yellow push out, you're gluing L and K together along I to get G. Whereas in the red one, you're gluing K and R together along I to get H. So yes, the idea is that you just want to kind of rewrite G to get H. So in particular, for our example, what we're doing is we're selecting a spin, so 5 in this case, and we're flipping it. So we're flipping it from orange to blue, and we're trying to calculate whether that is an accepted or rejected spin based off of like the temperature and all of that. And then we update it, or we don't, we leave it the same. So we have this code, which is now, I think, in under the algebraic Julia sort of name, and it's called combinatorial chains. So what it does is you specify temperature. So at the top, we specified T equals 1. You start with some random initial state, and then in the final state, depending on the temperature, you might get spins that are more or less aligned. And as you'd expect, at least if you're a physicist, you get sort of in the low temperature regions, you get spins tend to line up. And they try to minimize these domain walls between spin up and spin down, which is kind of what's happening at the top. And then also the energy drops, whereas at the bottom, you can see the energy kind of jumps around. Okay. But like I said, the Ising model is kind of well studied, and if this was the only thing it could do, it would be useless. So the motivation is that we can kind of look at any general type of combinatorial structure. So so we know that simplicial sets are C sets, and so you can speak about then Markov chains over these simplicial sets instead. And yeah, I think that's really cool. Yeah, so that's essentially what I just said here. And thanks. And I'd also just like to thank Sophie and David for organizing such a great school. Yeah.
Yeah, thanks, Amy, and thank you to Angeline and Kris and the entire Evan Patterson and James Fairbanks group. Okay, now for the final presentation, we have Simona Pauli's group, TA Mauro Sarazola, and the speakers will be Emma Phillips, Claire Art, and Elise McMahon on weakly globular double categories and Petri nets. Great.
Okay, so we're going to talk about kind of a couple different projects that we've worked on in the past week. And we're going to start just by introducing what weakly globular double categories are in general, and then talk about some ways that we've tried to use them in applications. So in general, we have kind of several notions of what we might mean when we talk about two categories. We have strict two categories, we have weak two categories or bicategories, and then we have these strict twofold categories or strict double categories. So very quickly, I'm going to stop saying strict double categories, but for our sake, when we say double categories, they're always strict, meaning that the horizontal composition is strictly associative and strictly unital. So we know that we can see strict two categories as living inside bicategories and living inside double categories. But the idea of weakly globular double categories is to see bicategories as living inside double categories as well. So we'll see that we can view double categories as simplicial objects in CAT. And so considering bicategories as living inside double categories means we can view bicategories that way as well. So all that simplicial data gives us the necessary coherence data of bicategories. And one of the things that's really powerful about that is that we can generalize all of this to higher dimensions. So working with bicategories, there's coherence data to check, but it's not terrible. If you try to work with tri-categories, checking the coherence data starts getting pretty terrible. And then when you get to weak n categories for n greater than 3, it's basically impossible. So being able to view this in terms of n-fold categories instead is going to mean that we can work with weak n categories in this model. So if we're going to think about a simplicial object in categories, a simplicial object in categories will be the horizontal nerve of a double category if and only if the Siegel maps are isomorphisms. And then a simplicial object in categories will be a strict two category if and only if the Siegel maps are isomorphisms and X0 is discrete. So if we want to think about finding a model for bicategories that lives in simplicial objects in categories, we want to weaken the properties of a strict two category, but we want it to stay as a double category. So we want to hold that the Siegel maps are isomorphisms, but we want to weaken this property that we require X0 to be discrete. So we end up defining weakly globular double category is a simplicial object in category where the Siegel maps are isomorphisms. In other words, that we do have a double category. And then we define this weak globularity condition, which is that we have this equivalence of categories between X0 and the discrete category of the path components of X0. And what this really means in terms of the double category is if you look at the category of objects and vertical morphisms, that's going to be a homotopically discrete groupoid. In other words, all the morphisms are isomorphisms, and there's at most one morphism between any pair of objects. And then the last condition we require is an induced Siegel map condition that we get this equivalence when we take the product over copies of X0 versus the product of copies of X1 over the discrete category of the path components of X0. And what that induced Siegel map condition actually gives us is that if we have these staircases in our double category, so these horizontal, vertical things, we can actually fill them in so that we can get map across of horizontal maps and these invertible two cells. And so Paoli and Franck proved that there's, well, defined weakly globular double categories and then proved that there's actually this biequivalence of two categories between weakly globular double categories and bicategories. So in other words, weakly globular double categories are a model of bicategories. And there are these actual functors that go big from weakly globular double categories to bicategories, which we call the fundamental bicategory. And then the double functor going back gives us the double category of marked paths. So given any bicategory, we can find the double category of marked paths associated to it. But what we want to do is to come up with a model of structured cospans in terms of weakly globular double categories. So we could look at the double category of marked paths, but what we've been trying to do is to develop an equivalent weakly globular double category where it's a little bit more transparent that we're dealing with cospans, and with the idea that we might be able to exploit the structured cospan model a bit more, or that we might be able to look at it in higher dimensions. So we start with a toy example rather than going straight to structured cospans. We look at the bicategory cospan, which has object discrete categories, one cells that are cospans in cat, where P is any category, not necessarily discrete, and our composition is given by pushouts. And two cells are these commuting diagrams. So when we put together this weakly globular double category, which we've been calling WSP, the general idea is that we want to start with a one cell in the cospan bicategory, so one of these cospans, and we want to come up with cospans in our weakly globular double category that will be generated by this cospan. So the first thing we need to deal with is the fact that horizontal composition in cospan is not strictly associative. So to handle that, we take isomorphism classes of the apex, which will make our horizontal composition strictly associative, since the composition here is associative up to isomorphism. However, of course, by taking the isomorphism classes of the apex, we're losing a significant amount of data. So we try to make up for that data by replacing the feet of our cospans with homotopically discrete groupoids x hat. So these groupoids are going to be roughly defined by creating these stars where the center of the star will be some point x from our original set. And each of the rays of the star that come out correspond to both functors from x to p and to natural isomorphisms of p, or of p to other isomorphic categories. And so we can break up the definition of these groupoids in two different ways. One, we could vary these groupoids over the elements in X, or we could vary it over the functors from X to P. And we've been playing with both of these models. We think that they both have their advantages. But one of the things is that every cospan from the original cospan bicategory will correspond to multiple cospans in the weakly globular double category. And then to verify that we've actually ultimately included the same data in our weakly globular double category, we verify that the fundamental bicategory of the weakly globular double category is biequivalent to our original cospan bicategory. So we've done that for one of the models, and we're still working on it for the other one. And I'm going to pass this off to Claire.
Thank you. So besides this construction of a weakly globular double category, we also looked at examples of applications, and for that looked at how we could make a weakly globular double category out of a Petri net with tokens. And so a token placement in a given Petri net is just a linear combination of places. So for example, we have this little Petri net here, and we have tokens placed on A and B. And then we can have a firing which exists for a transition where there is enough tokens placed on the source of the transition so that the transition can fire. And for example, here, this firing of tau would lead to a token placement on C and no tokens on A and B. And we can also combine firings if the token placements are coherent with the firings. And to construct our double category of Petri nets with token placements, we followed the construction of marked paths from a paper from Paoli and Pronk. And we looked at paths of token placement. So what I mean by this is, for example, for this little Petri net here, we start with a token placement on A, like we have 2 tokens on A, and then there occurs a firing. So we have a token on A and 1 on B, then 2 on B, and at last 1 on B and 1 on C. So that's one possible path of token placements. So for our objects in our double category, we take marked paths. And by this, I mean, we take one of those paths and we mark one specific token placement. So for example, for this path, we actually have 4 objects, one for each token placement marked. But we could also have different Petri nets. And for example, also for this Petri net, we can have different paths. And all of these give different objects in our double category. For the morphisms in our double category, we look at the horizontal morphisms. All the morphisms only occur between objects which have the same underlying Petri net. So for this example, we leave the Petri net fixed and don't include it in the diagram because it just gets messy. But yeah, so we have the same fixed Petri net in all these objects. So for example, for this object of the path we just saw, we have one object with the placement A and B marked, and we have another object with the placement B and C marked. And there is a morphism which goes along this path, and the morphism is the same path, but with 2 token placements marked. So yeah, you can see this here. And we have such morphisms between objects with the same path but different markings, but only along the path. So there is no morphism from the right-hand object back to the left-hand one. So it only goes forward, as long as the firing only goes forward. We also have vertical morphisms, and those we have also between objects with the same underlying Petri net, but we can have them with different paths. So here we have a different path. This path starts with a placement on A and B, and then goes another route, but also ends with a placement on B and C. And here we have the object with the same token placement marked. And so we only have one unique morphism between objects with the same underlying Petri net and the same marked token placement. And we always have one unique morphism between those objects. And we can fill in this square, and then we can also have a 2-cell. Our 2 cells exist between combination of firings, but only if we have this square, like where we have the same Petri net underlying and the same placements of tokens marked. And this gives us one weakly globular double category of Petri nets with token placements. And I'm going to give over to Elise to share what more ideas we have with that.
Cool. Can you see my slide? Okay, great.
Yeah.
So I'm just going to say a few words about sort of where we're taking this in the future. So one of our goals, of course, is going to be to find examples of what this weakly globular double categories can model, especially like comparing between models of just regular double categories to see kind of what this extra or what this weak globularity can encode. So one very general idea that we had was that maybe these the star, I guess Emma didn't refer to this, I don't remember if she referred to the stars, but in the apexes were sort of fattening each elements by this groupoid. You can imagine it looking like little stars, with the center being what our object in X was. So we're thinking that maybe this fattening can correspond to like small deformations of the apex. So for example, if we were extending this to Petri nets modeling this with Petri nets with rates, we could maybe realize these stars as corresponding to small deformations in the rates. So that's sort of one idea we have for interpreting the notion of weak globularity. And then just some general questions that we have is if we can extend this model to cospans from other categories. So just general category with pushouts. If we can consider the analog of weakly globularity in n-fold categories, which is what Emma referred to as one of the nice things about this construction, is that it should lend itself more easily to extending to higher categories. And then if you noticed in Claire's example, each of the all of the structure of the double category is like in a connected component, so you don't have any morphisms between different Petri nets. So the idea is maybe there's a way to weaken this notion so that we can have morphisms between Petri nets, or maybe this would naturally fall out of a higher category, like a threefold category. And then a last question we want to pursue, and if anyone has ideas that they want to let us know on these questions, is if there's a way to interpret, other ways to interpret the notion of weak globularity, especially in terms of cospans. Here's our references, and thank you.
Yeah, thank you, Elise, and Emma and Claire too. So just to close, this brings us to the end of the session. I'll just say that the Adjoint School is a major teaching and community building project, and while it's lots of fun, it does involve significant amounts of volunteer work from the teaching and organizing teams. So I'd like to quickly just acknowledge the mentors and TAs. So the mentors, James Fairbanks, Hella Hansen, Clemens Kupke, Simona Pauli, Evan Patterson, and Simon Willerton. And the TAs this year, Titan A. Bradley, Owen Lynch, Callum Reeder, Myra Salazzola, Toby Smith, and Christian Williams. So thank you all for your amazing work. I know that the students are very, very grateful too. Yeah, it's been a joy listening to all the presentations today and all the work that's been going on over the past week and the 6 months of preparation before that. And I really look forward to reading the papers as they emerge in the coming months. But finally, I think it's really important that we acknowledge the organizers. It's really a gigantic effort. Starting, it's a 12-month project, starting with designing the school and putting up the website and recruiting but mentors, TAs, and students, going through the selection process, keeping up to date with all the reading. Most groups just have to concentrate on 2 readings. The facilitators and organizers have to read all 8 and run the online forum and discussions, chase blog posts, and organize the session today. So to Sophie Libkind and David Jasmyers, just thank you. It's amazing the work you've done. Okay, and with that, I will end the session, but I think the room can remain open if people want to discuss anything. I'm happy to moderate questions for a bit if that's something people would like to do. Maybe we'll take some guidance from the headquarters in Cambridge.
We need to clear the lecture hall because, great, yeah, COVID restrictions. So thanks a lot. But we can leave the Zoom room open, I think.
Cool.
Thank you.
Well, thanks everyone.
a lot.
Great job, everyone.
Thanks a lot to you guys. It was really, I mean, the amount of work you did and I mean, how well organized this event was really, really impressive. So yeah, you can really be proud and satisfied with how things went, I think. Really nicely done.
Thank you.
Thank you.
Yeah, I know. Well, who's still here? It's been a busy period. I think everyone just needs a bit of a break and time to maybe enjoy this conference. Yeah, I really enjoyed listening to everyone's talks today, and I hope the work goes further. It'd be lovely at some point to have some sort of debrief session, I think, about the school too, if anyone has any thoughts they'd like to share just about how the experience of it, anything to improve for next year, ways to get involved. But I think we'll organize that once we've had a bit of a breather. So thanks again.